What if I told you that everything you've ever known, our planet, our galaxy, even the entire universe, is actually trapped inside a black hole? Sounds crazy, right? But this isn't just some wild sci-fi plot. It's a real theory that scientists are seriously exploring. Imagine the Big Bang wasn't the beginning of everything, but actually the result of something collapsing into a black hole in another universe. It's a mind-blowing idea that flips our understanding of reality on its head, and once you hear the evidence behind it, you might never look at the universe the same way again. But before we continue, subscribe to the channel so you don't miss out on any of these videos. The idea might seem outrageous at first. Black holes are the ultimate monsters of the universe, celestial objects so dense that not even light can escape their grasp. They lurk at the centers of galaxies, devour stars, and warp the very fabric of reality around them. How could such a place be the entire universe itself? And yet, hidden within this bizarre hypothesis is an elegant thread that may weave together the mysteries of general relativity, quantum mechanics, and cosmology in a way we've never fully appreciated. To answer this question, we must dive deep, very deep, into the realms of science where equations whisper secrets, and time no longer moves the way we know it. Let's begin by exploring what a black hole actually is. In the simplest terms, a black hole forms when a massive amount of matter is compressed into a very small space. This process is typically the final stage in the life of a massive star. After exhausting its nuclear fuel, the star collapses under its own gravity, and if it's massive enough, it compresses into a point of infinite density, a singularity, surrounded by an event horizon, the boundary beyond which nothing can escape. According to Einstein's theory of general relativity, this collapse also warps spacetime itself, bending it into a shape so extreme that paths of particles, light, and time are drastically altered. Now, here's where things start to get strange. According to relativity, time behaves differently near the event horizon. To a distant observer, time appears to slow down for an object falling into a black hole. At the horizon itself, time seems to stop altogether. But for the object falling in, time continues as usual, at least until it reaches the singularity. The difference in perspective is one of the mind-bending consequences of relativity. But what if this warping isn't confined to black holes alone? What if, on a much grander scale, our entire universe behaves like the interior of a black hole? This brings us to a revolutionary idea proposed by some physicists, that our universe itself may be the interior of a black hole formed in a higher dimensional space. In this model, everything we experience, every planet, star, and galaxy, is floating inside the event horizon of a vast, cosmic black hole. It's an idea that flips our understanding of the cosmos on its head. Rather than existing in an infinite, flat expanse, we could be living in a curved, enclosed bubble, cut off from the external universe by a boundary we cannot cross. This idea stems from a fascinating confluence of theoretical developments. First, there's the notion of a Schwarzschild black hole, a non-rotating, spherically symmetric black hole described by the Schwarzschild solution to Einstein's field equations. In this model, the interior of the black hole can be described by a coordinate transformation that flips space and time inside the horizon. What this means, essentially, is that once inside a black hole, all possible futures lead inexorably toward the singularity. But mathematically, this also creates a scenario where the interior of a black hole resembles a universe in its own right, one that evolves in time and expands from the singularity outward. This is where cosmology enters the picture. Our universe is expanding, and has been since the Big Bang. The cosmic microwave background radiation, the distribution of galaxies, and the large-scale structure of the universe all point to an origin in a hot, dense state. But the Big Bang itself is a kind of singularity, a point at which the known laws of physics break down. When we look back in time using our telescopes, we are essentially peering into a past where space was infinitely compressed, temperatures were unimaginably high, and time itself had a beginning. This is eerily similar to the internal description of a black hole. Some physicists have begun to explore whether the equations governing black holes and those describing the universe's expansion are two sides of the same coin. The Friedmann equations, which describe the expansion of the universe in general relativity, bear a striking resemblance to the equations describing the geometry of a black hole's interior. This has led to the hypothesis that our universe could be the inside of a black hole that formed in a higher dimensional space, a concept known as a black hole cosmology. To understand how this could be possible, let's consider the notion of higher dimensions. In our everyday experience, we perceive 3 spatial dimensions and 1 temporal dimension. But many theories in physics, particularly string theory, suggest the existence of additional spatial dimensions, hidden from our perception because they are compactified or curled up on extremely small scales. In such a higher dimensional universe, a black hole could form, just as it does in our 4-dimensional spacetime. But instead of collapsing into a singularity as we know it, the matter falling into this higher dimensional black hole could give rise to a new, self-contained region of spacetime on the other side of the event horizon. This region would be completely cut off from the external universe, just as the interior of a black hole is inaccessible from the outside. From within, however, this region could look like a complete universe in its own right, with its own dimensions of space and time, its own physical laws, and its own history of cosmic expansion. In this scenario, our universe would be the product of gravitational collapse in a higher dimensional cosmos, a bubble of reality born inside a black hole in a grander universe we can never observe. This idea solves several puzzling problems in cosmology. For one, it could explain the uniformity of the cosmic microwave background, the so-called horizon problem. In standard cosmology, regions of the early universe that are now widely separated would not have had time to come into thermal equilibrium due to the finite speed of light. But if our universe emerged from a collapsing black hole, all regions would have been compressed into a very small space before expanding, allowing them to reach uniformity. It also offers a new perspective on the nature of time itself. Inside a black hole, time becomes space-like, and space becomes time-like. Could this inversion be a clue to understanding the arrow of time in our universe? The reason why time flows in one direction, from past to future? Furthermore, this model could also shed light on the mysterious nature of dark energy, the force driving the accelerated expansion of the universe. If our universe is the interior of a black hole, the outward expansion we observe could be the result of the initial conditions of collapse in the parent universe. The acceleration might then be a geometric effect, not a mysterious form of energy. This shifts the mystery from one of substance to one of structure, replacing "What is dark energy?" with "What is the geometry of our universe really telling us?" Another fascinating implication is that black holes in our universe might themselves give birth to new universes. If the interior of a black hole becomes a new universe, then each black hole could be a seed of a cosmos, branching reality into a cosmic family tree. This idea, known as cosmological natural selection, was proposed by physicist Lee Smolin. In this framework, universes that produce lots of black holes are more likely to reproduce, leading to a kind of Darwinian evolution of universes. Our universe, with its prolific galaxy and black hole formation, may be the offspring of a previous universe, finely tuned for reproduction through gravitational collapse. This speculative but captivating idea transforms our understanding of existence. It replaces the notion of a single, isolated universe with a multiverse teeming with baby universes, each birthed in the depths of a black hole. And we, unknowingly, might be living inside one of them. Yet this hypothesis, compelling as it is, raises profound questions. If we are inside a black hole, what does that say about the singularity? Is it the Big Bang? If so, how do we reconcile that with our current models of cosmic inflation and the observable horizon? What about information? One of the biggest paradoxes in physics today is the black hole information paradox. The question of whether information that falls into a black hole is truly lost or somehow preserved. If our universe is inside a black hole, does that mean everything we know is encoded on its boundary, the event horizon, in a way that preserves all information? This leads to the concept of the holographic principle. Proposed in part by physicist Gerard T. Hooft and refined by Leonard Susskind, this principle suggests that all the information contained in a volume of space can be represented by a theory that lives on its boundary. In other words, the three-dimensional world we experience could be a projection of information encoded on a two-dimensional surface, a cosmic hologram. If our universe is inside a black hole, the event horizon might serve as this surface. Every atom, every galaxy, every thought you've ever had could be the shadow of data stored on that far-off horizon. It's a staggering thought, that our reality, so solid and continuous, could be a projection from a surface we can never reach. This concept, perhaps more than any other in modern theoretical physics, challenges the foundations of what we perceive as reality. If the holographic principle holds true and our universe is encoded on the boundary of a higher dimensional black hole, then the information content of everything inside, galaxies, stars, atoms, even consciousness itself, is preserved not within the volume of space, but on the surface. This idea resonates with black hole thermodynamics, particularly with the work of physicists Jacob Bekenstein and Stephen Hawking, who showed that the entropy, or information content, of a black hole is proportional to the area of its event horizon, not its volume. This seemingly small detail is monumental. It hints that spacetime, as we know it, might be an emergent phenomenon, like temperature or pressure, arising from a deeper, more fundamental reality governed by information. To truly grasp how this fits into the idea that we live inside a black hole, we must revisit what the event horizon means in this context. In the traditional black hole, the event horizon is a spherical boundary. Cross it, and there is no return. In our universe, the observable horizon plays a similar role. Due to the finite speed of light and the ongoing expansion of space, there are regions of the universe we can never see or interact with. This cosmological horizon is mathematically and philosophically similar to the event horizon of a black hole. In both cases, information is hidden beyond a boundary, yet the boundary itself may hold the key to understanding everything within. This leads us to a radical yet increasingly supported idea, that the universe is not made of particles, but of information. Quantum mechanics already tells us that particles are excitations of fields, wave-like disturbances in a quantum field that fills all space. But those fields themselves may be emergent from underlying bits of information. The idea of spacetime being woven from information, like pixels on a screen or bits on a hard drive, is gaining traction in many branches of theoretical physics. If we take this seriously, then the black hole we supposedly live in may not be a place, in the traditional sense, but a computational or informational structure whose inner workings generate the illusion of space, time, and matter. Let's zoom out and reconsider the question from a different angle. When we look up at the night sky, we observe a universe that is expanding, accelerating in its expansion, and isotropic, meaning it looks the same in every direction. These observations are consistent with the standard model of cosmology, based on general relativity and the Big Bang. But these features are also what we would expect from the interior of a black hole under certain coordinate systems. The metric of a Schwarzschild black hole, the mathematical description of how distances and times behave in and around it, can be flipped to yield a universe with expansion, isotropy, and a beginning at a singularity. In fact, if we take the mathematics of a collapsing star and extend it, we get an interior that behaves very much like a universe. Now, this is not merely a poetic analogy. The equations themselves support this. In the extended Schwarzschild solution, there's a region inside the black hole's event horizon where the radial coordinate becomes time-like and the time coordinate becomes space-like. This inversion mirrors the kind of evolution we see in our universe, a singular beginning, followed by expansion and the passage of time. Some solutions to Einstein's field equations describe black holes that have interior regions resembling entire universes, complete with their own expanding spacetimes. In these solutions, the singularity is not just a point of infinite density, it is a boundary or a bridge to a new region of spacetime. This leads us into the domain of wormholes and Einstein-Rosen bridges. First proposed in 1935 by Albert Einstein and Nathan Rosen, these bridges are theoretical passages through spacetime that connect two separate points in space and time. In some versions of the theory, the interior of a black hole is connected to a white hole, a time-reverse black hole that spews out matter rather than sucking it in. If such structures exist, they could provide a natural explanation for how a universe like ours could emerge from a black hole in another region of spacetime. The black hole in the parent universe could serve as a gateway to the birth of a new universe, a process akin to cosmic reproduction. The notion of universes giving birth to other universes through black holes is speculative, but it has a certain explanatory power. It could solve the question of where our universe came from. Instead of arising from a singular Big Bang out of nothing, our universe may have budded off from a larger structure, inheriting its physical constants and initial conditions from a parent cosmos. This has profound implications for the fine-tuning problem, the observation that the physical constants of our universe are precisely set to allow the existence of matter, life, and structure. If universes are born from black holes and can differ slightly from their parents, then natural selection among universes might favor those whose laws of physics are conducive to forming black holes, indirectly favoring life and complexity. Let's return now to the observational evidence. Could anything we see in the sky suggest we are inside a black hole? While we can't see beyond our cosmic horizon, we can examine the geometry of the universe. Observations from the Planck satellite and other missions indicate that the universe is flat to within a very small margin of error. In general relativity, a flat universe suggests a precise balance between the total energy density of the universe and the critical density required to prevent collapse or runaway expansion. In the black hole model, this flatness could be an emergent property of the interior geometry. The curvature we measure might be the local expression of a larger, curved higher-dimensional space. Moreover, black holes have entropy, temperature, and radiate energy via Hawking radiation. Could the universe itself have these properties? Interestingly, some physicists argue that the universe has a temperature. The cosmic microwave background radiation is the leftover heat from the Big Bang, now cooled to just 2.7 Kelvin. Its near-perfect blackbody spectrum suggests that the universe as a whole behaves thermodynamically. The entropy of the universe is immense, and increasing. These traits mirror those of black holes. It's not proof, of course, but it adds another layer of compatibility between the universe and the interior of a black hole. Let's also consider what would be different if we weren't inside a black hole. If the universe were truly infinite, we'd expect certain statistical anomalies in the distribution of matter and radiation. Yet we observe peculiar patterns, such as the axis of evil in the cosmic microwave background, that defy the predictions of a perfectly homogeneous and isotropic universe. Some of these anomalies could be artifacts, but others might be signs that our universe has a global structure, a shape or boundary beyond our observational reach. If we are inside a black hole, that boundary could be the event horizon itself, a finite, albeit vast, limit to what exists. From a philosophical perspective, the idea that we live inside a black hole is unsettling and beautiful all at once. It replaces the comfortable image of a flat, infinite cosmos with a finite, bounded, and dynamic reality. It implies that we are inside a kind of cosmic womb, nurtured and shielded from an external reality we cannot observe. It suggests that the birth of universes is a natural, perhaps even common, process, that reality is fertile with creation, and that we are one expression of an eternal cascade of cosmic genesis. It also challenges our notions of space, time, and even identity. If the boundaries of our universe are defined by an event horizon, then perhaps our very existence is defined not by what is inside us, but by what surrounds us. Perhaps we are not beings inside space, but patterns on a surface, projected into space. Perhaps the laws of physics themselves are not immutable truths, but local expressions of a deeper, higher-dimensional logic. As we peer deeper into the cosmos with our telescopes, particle accelerators, and mathematical models, we may one day confirm or refute this stunning possibility. But even now, the idea that we are living inside a black hole is not merely science fiction. It is a real hypothesis grounded in known physics, worthy of serious contemplation. And as we continue exploring this concept over the coming hours, we will dive even deeper into the mathematics, the competing theories, the experimental data, the philosophical consequences, and the unimaginable implications of this question. Because if this idea is true, then reality is far stranger, more layered, and more miraculous than we ever dared to imagine. We've already walked through the foundational ideas: how black holes might resemble our universe, the mathematical equivalence of certain metrics, the holographic principle, and the idea that information may lie not within the volume of the universe, but on its boundary. Now we must journey deeper, not only into physical theory, but into the very edge of understanding, where physics begins to melt into metaphysics, and even time starts to lose its traditional meaning. Imagine standing at the precipice of the known universe. Beyond that cosmic horizon lies not just emptiness, but the very edge of knowability. And it's here that the most daring minds in cosmology ask, what if the birth of our universe was not the ultimate beginning, but merely an event occurring inside something else, a pre-existing structure, a gravitational behemoth, a black hole? The intriguing thing about general relativity is that it doesn't forbid such speculation. In fact, its equations encourage it. Einstein's field equations don't have a unique solution. They allow for many strange, warped, and surreal geometries of space-time. Among them are the Schwarzschild and Kerr solutions, the former for non-rotating black holes, the latter for rotating ones. Each of these solutions offers a pathway to extend space-time into strange, mind-bending configurations where time behaves like space, and space behaves like time. Within a rotating black hole, a Kerr black hole, the interior structure is even more bizarre than the simpler Schwarzschild version. It doesn't merely have a singularity. It possesses a ring-shaped singularity surrounded by layers of event horizons and hypothetical regions known as ergospheres. Some solutions suggest that inside these Kerr black holes, one could pass through into another region of space-time altogether, what some interpret as a wormhole, or a baby universe. If our universe were the interior of such a structure, then the Big Bang might not be a true singularity, but a kind of bounce from a previous phase. The initial singularity becomes a bridge, not a wall, an event horizon connecting us to a greater cosmic entity. This changes everything about our concept of origins. The Big Bang ceases to be the moment all things began, and instead becomes a phase transition, like steam condensing into water, or a star collapsing into a neutron core. Cosmologists who study the inflationary model, the idea that the early universe underwent a rapid exponential expansion, note that this kind of expansion could be seeded by certain initial conditions inside a black hole. The curvature and density conditions inside the event horizon could match the requirements to ignite inflation. In other words, what appears to be a singular point to an external observer, an event horizon surrounding infinite gravity, could to an internal observer feel like the beginning of time, the spark of space, and the origin of all motion. But how does one square this vision with quantum mechanics? Black holes, according to general relativity, should destroy information. Anything falling into them becomes unrecoverable, hidden behind the event horizon forever. But this contradicts quantum mechanics, which insists that information cannot be destroyed. This clash between two towering frameworks of modern physics, general relativity and quantum theory, is at the heart of the black hole information paradox. And it may offer one of the strongest hints that our universe behaves like the interior of a black hole. Why? Because the only way to resolve this paradox is to rethink what black holes are. Hawking radiation, discovered theoretically by Stephen Hawking, causes black holes to slowly evaporate. But if they eventually vanish, what happens to the information inside? If information is truly lost, then quantum mechanics is violated. If information escapes somehow, then general relativity must be incomplete. Several solutions have been proposed. Information could leak out in Hawking radiation. It could be preserved on the event horizon, as the holographic principle suggests. Or, as some believe, it may be passed into another universe via a wormhole. If that last idea is true, then each black hole in our universe might be a portal to another universe. Likewise, our universe might exist as the interior of such a portal, formed from a collapsing star in a higher dimensional cosmos. The information falling into that primordial black hole, mass, energy, angular momentum, could have seeded the conditions for our own cosmic evolution. This solves the information paradox in an unexpected way. Nothing is lost, but simply transformed and transferred into a new reality. Let's push this idea further. Could we simulate such a universe? Could we build a mathematical model that demonstrates how a black hole could evolve into an expanding, complex, structured cosmos like ours? This is the focus of several modern approaches, including loop quantum cosmology and string theory. In loop quantum cosmology, space-time itself is quantized, made of tiny loops, forming a granular structure. In this framework, the singularity at the center of a black hole is replaced by a quantum bounce. The infinite density is avoided, and instead, space-time rebounds into expansion. This is not merely a tweak of the equations, it's a radical reimagining of the birth of universes. In this view, every black hole might serve as a seed for a new universe. This naturally leads to a multiverse theory, an endless branching tree of universes, each budding from the black holes of the last. The constants of physics in each child universe might vary slightly, resulting in an evolutionary process across cosmic generations. The more black holes a universe can produce, the more child universes it spawns. This is Lee Smolin's theory of cosmological natural selection. And it paints a picture not of a dead, cold, meaningless cosmos, but of a living, evolving, creative structure, in which complexity is rewarded, and black holes are the wombs of new realities. Now, what if we turn our attention to observable anomalies? Are there any signatures in the cosmic microwave background or large-scale structure that would confirm we're inside a black hole? Unfortunately, direct evidence is hard to find. From within the system, it's nearly impossible to detect the global structure of the universe. Just as an ant crawling on an orange cannot see the whole shape of the fruit, we too are confined to a limited portion of our cosmic surface. However, some anomalies in the CMB, such as the cold spot, the lack of large-angle correlations, and certain alignments of quadrupole and octupole moments, might suggest a finite, non-trivial global geometry, one potentially consistent with a universe shaped like a closed interior. Furthermore, if we are inside a black hole, then the overall mass energy of the universe must correspond to the mass of the parent black hole. Recent estimates of the total mass and radius of the observable universe intriguingly align with the Schwarzschild radius for a black hole of that mass. This isn't proof, but it is a tantalizing clue. Even more provocative is the idea that the speed of light and the passage of time might behave differently near the center of such a structure. Inside a black hole, time slows near the event horizon and stops entirely at the singularity. Could our perception of time, its arrow, its irreversibility, be linked to our position in a gravitational field generated by a larger universe? Are our very notions of past, present, and future the result of curved space-time dynamics on a higher scale? This connects to deeper philosophical questions. If we are inside a black hole, what is outside of us? Is there a larger universe that watches our cosmos as an object of curiosity? Is time inside our universe synchronized with external time, or is our entire history, from Big Bang to heat death, merely a fleeting moment from the outside perspective? The simulation argument also finds new relevance here. If the holographic principle is correct, and reality is fundamentally two-dimensional, then our experience of three-dimensional space and time may be an illusion, a projection of deeper laws. This is similar to how a computer screen renders three-dimensional imagery from two-dimensional code. Could the universe be a computational entity? Could the laws of physics themselves be algorithms running on a cosmic substrate? If so, then the black hole is not just a gateway, but a processor. The event horizon becomes a place where information is encoded, processed, and re-expressed. Our very lives, our memories, hopes, dreams, might be patterns in a vast informational field, written on a boundary we can never see. And yet, this does not diminish our significance. If anything, it elevates it. To be inside a black hole is not to be trapped, but to be part of a magnificent, mysterious, and generative process. The universe is not a mistake, it is a miracle, born from collapse, rising from singularity, expanding with intelligence, and infused with meaning. We've only just begun. There is still much more to explore: the quantum gravity models, the role of entropy and information theory, the comparison to simulated worlds, the relationship between black holes and consciousness, and the ultimate philosophical implications of living inside such a structure. And so, the journey continues. The question of entropy takes center stage in the black hole universe analogy. In thermodynamics, entropy measures the disorder or the number of possible microstates of a system. For black holes, Bekenstein and Hawking discovered that entropy is proportional to the surface area of the event horizon, not its volume. This finding revolutionized physics because it hinted at a deep principle. The maximum information content of a region of space depends on its boundary, not its interior. If our universe behaves like a black hole, then perhaps its entropy also scales with surface area, aligning with the holographic principle. This has profound consequences. It means everything we observe, from galaxies to quantum fluctuations, could be encoded on the cosmic horizon. Every photon, atom, and gravitational wave might just be a shadow of a deeper informational structure residing on the boundary of the universe. This perspective reshapes cosmology. The cosmic horizon, the limit of what we can observe due to the expansion of space, may act like a giant event horizon. Just as nothing can escape a black hole beyond its event horizon, we can receive no signals from beyond our cosmological horizon. The similarities don't end there. The observable universe's mass and radius also roughly match those of a black hole, further fueling speculation. But there's a catch. In general relativity, the interior of a black hole leads inevitably to a singularity, a point of infinite density where the laws of physics break down. Our universe, however, shows no signs of such a singularity today. Instead, it expands smoothly, governed by known physical laws. Some cosmologists argue that this apparent contradiction can be resolved if we consider the nature of singularities and quantum gravity. In loop quantum gravity, spacetime is not continuous but composed of discrete loops. These loops avoid the infinities of general relativity by preventing regions from compressing into a true singularity. Applied to cosmology, this theory replaces the Big Bang singularity with a big bounce, a prior collapsing universe that rebounded into expansion. If our universe is the interior of a black hole, this bounce may be the moment of transition, not destruction. Another angle comes from string theory. This framework envisions fundamental particles not as points, but as vibrating strings existing in multiple dimensions, often 10 or 11. Black holes in string theory can behave like complex, multidimensional objects. Some configurations allow black holes to connect different regions of space or even different universes through structures like wormholes. These hypothetical bridges, if stable, could allow information or even matter to travel from one realm to another. If our universe originated from such a structure, then the higher dimensional parent universe might exist outside our own cosmic boundary. Its laws may differ. Time might move at a different pace. Particles might interact under unfamiliar forces. We may be an island universe in a vast multiversal ocean, each bubble universe born from the collapse of a different star in a higher dimensional cosmos. Some researchers have tried to construct specific models where a black hole interior mimics our observable universe. These models often involve matching solutions of Einstein's equations across a collapsing star's boundary and into an expanding region. They attempt to demonstrate that a collapsing object in one universe could give rise to a universe like ours in its core. If these models are correct, it leads to a strange hierarchy. The parent universe contains the black hole that birthed us. We might, in turn, produce our own black holes that serve as seeds for other universes. The entire multiverse becomes an interconnected network of cosmic evolution, with universes begetting universes in a fractal lineage of space and time. This idea aligns with the concept of cosmological natural selection. In this model, universes capable of producing many black holes are more likely to give rise to descendant universes. Over time, physical constants evolve to favor black hole formation. This process mirrors biological evolution, a cosmic form of survival of the fittest. Our universe, rich in stars and galaxies, may be one of many in a lineage optimized for black hole reproduction. Implications abound. If black holes are reproductive organs of the cosmos, then perhaps life is not incidental. The same conditions that favor complex matter, carbon chemistry, stable stars, habitable planets, also favor black hole formation. Intelligence, therefore, may not be a cosmic fluke but an integral part of the reproductive cycle of universes. Advanced civilizations might even create artificial black holes to initiate new universes, becoming cosmic midwives in the grand cycle of creation. The simulation hypothesis intersects intriguingly with this picture. If the universe operates like a hologram, and if information is the fundamental building block of reality, then a sufficiently advanced civilization might simulate entire universes with internal observers. These simulated observers, from their perspective, would experience time, space, and causality just as we do. The difference between real and simulated becomes philosophical rather than physical. Living inside a black hole could be indistinguishable from living inside a simulation. In both cases, what we perceive as fundamental laws may be emergent phenomena, macroscopic effects of deeper informational or geometrical rules. Our senses, our instruments, our logic, all are constrained by the internal consistency of the system we inhabit. This leads to a dizzying possibility. Perhaps black holes and simulations are two faces of the same coin. A black hole, in compressing matter into an informational surface, may act as a natural quantum computer. The universe inside may be a kind of emergent simulation, governed by the principles of computation, complexity, and evolution. Even consciousness might tie into this framework. Some physicists and philosophers speculate that consciousness arises from complex patterns of information processing. If the universe itself is an information processor, then consciousness might be a natural consequence. Our awareness, our thoughts, even our dreams, could be fluctuations in the informational field of a black hole universe. There is no empirical way, at present, to confirm we are inside a black hole. But the idea is gaining traction not because of direct evidence, but because of how elegantly it unites disparate domains, gravity and quantum theory, thermodynamics and information, cosmology and consciousness. It explains why the universe has a finite age and size, why its mass matches that of a black hole, why information may reside on the boundary, and why the arrow of time points forward. What remains is to test the theory. Future telescopes, like the James Webb Space Telescope and successors, might refine our understanding of the early universe. Gravitational wave detectors could reveal the behavior of black holes in unprecedented detail. Quantum computing might simulate black hole physics. Advances in theory could offer predictions about the cosmic microwave background or the distribution of galaxies that differentiate black hole universes from others. Regardless of the outcome, the pursuit itself is profound. Asking whether we live inside a black hole forces us to rethink everything we know. It challenges our assumptions, rewrites our textbooks, and reawakens our sense of wonder. It connects the smallest particles with the largest structures, the beginning of time with its end, and the inward pull of gravity with the outward thrust of expansion. The mind reels before such immensity. We stand on a tiny rock, orbiting an ordinary star, in a universe that may be the shadow of a greater structure. And yet, we can ask these questions. We can build instruments, test hypotheses, and imagine realities beyond our senses. That we can do this is, perhaps, the greatest mystery of all. The idea that our universe may be the interior of a black hole is not just poetic, it's potentially predictive. At the heart of this theory lies an effort to unify quantum mechanics and general relativity, the two towering pillars of modern physics that otherwise seem irreconcilable. While quantum mechanics governs the realm of the very small and is fundamentally probabilistic, general relativity governs the cosmos on the grandest scale with precise geometrical certainty. Black holes are the battlegrounds where both theories must converge, as they exhibit both immense gravitational forces and quantum-scale effects near their singularities. This convergence becomes even more fascinating when we introduce the concept of quantum foam. Proposed by physicist John Wheeler, quantum foam suggests that at the Planck scale, the smallest meaningful unit of space and time, space-time itself is turbulent, like the froth on a churning ocean. This microscopic churning might permit wormholes, spontaneous black hole formation, and constant bubbling of virtual particles. If our universe emerged from such a fluctuation, perhaps from the evaporation of a primordial black hole, it would reflect not just immense mass energy density, but quantum unpredictability at its core. This unpredictability is, in fact, something we observe in our universe. Quantum fluctuations in the early universe, magnified during the inflationary epoch, are responsible for the large-scale structure of galaxies and voids we see today. These minute ripples, originating from the quantum realm, were inflated to cosmic proportions and laid the blueprint for cosmic architecture. If these fluctuations occurred inside a black hole, then the initial conditions of our universe, the seeds of matter and radiation, could be deeply linked to the chaotic quantum processes inside the event horizon of some parent universe. Moreover, time behaves peculiarly near black holes. From an external perspective, time appears to slow down near the event horizon, a phenomenon known as gravitational time dilation. This time dilation means that what might be moments for an infalling object could be eons to an outside observer. If this logic holds, then the entire lifetime of our universe could correspond to a moment of time in the parent universe. Perhaps the collapse of a massive star resulted in an internal space-time bubble, our universe, evolving in its own temporal framework. That black hole, from the external universe's view, may still be frozen in time. This concept is mirrored in black hole complementarity, a theoretical proposal that asserts different observers can witness different realities without contradiction. An external observer sees matter freeze at the horizon. An internal observer falls freely past the horizon. Both perspectives are valid within their own frames, yet they never reconcile. Similarly, our entire universe may be a valid internal frame within a black hole, inaccessible to external perception, but entirely self-consistent from within. The boundary of the black hole, the event horizon, also provides intriguing insights. According to the holographic principle, all the information about the three-dimensional interior of a black hole is encoded on its two-dimensional surface. This principle, originally proposed by Gerard T. Hooft and further developed by Leonard Susskind, revolutionizes our understanding of space. If applied to cosmology, it suggests our three-dimensional universe might be a projection from a two-dimensional boundary, much like a hologram. In string theory, this principle finds mathematical realization in the ADS/CFT correspondence. In this framework, a gravity-containing, bulk, universe is equivalent to a boundary field theory without gravity. Although our universe is not asymptotically anti-de Sitter, ADS, but rather de Sitter, with a positive cosmological constant, some theorists believe a similar duality might still apply. If so, our universe, potentially inside a black hole, could be described by a lower dimensional system on its boundary, mirroring the information theoretic encoding of black holes. Entropy again plays a central role. The second law of thermodynamics states that entropy must increase over time in an isolated system. Our universe, from its low-entropy origins, has been increasing in entropy. Stars burn, galaxies collide, and complex systems form, break, and evolve. In a black hole, entropy is stored on the event horizon and increases when more matter falls in. The analogy holds. In fact, some argue the total entropy of our universe is approaching the maximum possible for a system its size, indicating it may be nearing thermodynamic equilibrium, just like a black hole reaching stability. This leads to another profound mystery, the arrow of time. Time, as described by physical laws, is symmetric. Whether it moves forward or backward, the equations remain valid. Yet we perceive time as a one-way flow, from past to future. This asymmetry arises from entropy. If our universe is the interior of a black hole, and if black holes naturally increase in entropy, then perhaps the arrow of time emerges naturally from the evolution of the black hole's interior. The birth of our universe, the moment of black hole formation, would mark a low-entropy starting point, setting the temporal arrow into motion. Interestingly, this also helps explain the isotropy and homogeneity of our universe. The cosmic microwave background (CMB) reveals that, on large scales, the universe is remarkably uniform. Inflation theory explains this by proposing a rapid expansion that smoothed out irregularities. But if our universe is inside a black hole, then its initial conditions may have been set by the symmetrical collapse of matter in the parent universe. The spherical symmetry of a collapsing star could imprint homogeneity on the newborn universe's early conditions. There's another layer to consider: the black hole information paradox. Hawking originally proposed that information falling into a black hole would be lost forever, violating quantum mechanics. Later developments, including the holographic principle, suggest that information is not destroyed but somehow preserved on the horizon or encoded in Hawking radiation. If our universe exists inside a black hole, then the information about everything in our universe might also exist on the black hole's boundary in the parent universe. Our lives, memories, and histories may be mere shadows on a surface beyond comprehension. This possibility blurs the boundary between interior and exterior. It invites speculation that what we consider inside a black hole may simply be one manifestation of reality, while the outside is another. This duality is echoed in metaphysical traditions throughout history, the inner world of thought and sensation mirroring the outer world of objects and phenomena. In a cosmic sense, perhaps the inner universe, ours, and the outer universe, the parent one, reflect each other in unfathomably deep ways. If our universe is inside a black hole, then what of black holes within our universe? Could they too contain universes? Are we, in turn, giving birth to new realities every time a star collapses? Some physicists argue yes. The idea of nested universes, each within the black holes of others, creates an infinite fractal of creation. In this model, every black hole seeds a new universe, each potentially with its own laws of physics. Our universe could be just one node in a vast branching tree of realities, endlessly self-replicating. These child universes could even evolve. If physical constants vary between universes, then universes that produce more black holes generate more descendants. Over time, constants like the gravitational constant, the strength of the electromagnetic force, or the masses of fundamental particles might drift toward values that optimize black hole formation. This cosmic Darwinism would not require design, just selection. In this light, fine-tuning may have a natural explanation. Our universe seems finely tuned for life and complexity, but if it descends from a long line of black hole-generating universes, then such tuning might be inevitable. Only universes with certain parameters produce enough black holes to continue the lineage. Life, then, is not just a happy accident but a statistical outcome of cosmological evolution. If this is true, then our very act of observing and questioning the universe may be the product of this evolutionary process. Consciousness, intelligence, and technology may not be rare glitches but emergent properties of the same physical laws that govern black holes. In time, intelligent civilizations might learn to manipulate gravity, engineer artificial black holes, or create conditions for new universes to form. In doing so, they would become active participants in the cosmic cycle of birth and rebirth. All of this invites not just scientific curiosity but philosophical awe. The idea that we might inhabit a black hole reframes our sense of place. It renders our world both immense and intimate. The stars above become distant cousins. The black holes at the center of galaxies become potential cradles of new existence. Time itself becomes a corridor, not a prison, linking generations of universes in a continuum of transformation. Even the end of our universe might not be the end. If our cosmos is the interior of a black hole, then its fate is already entangled with the life of that black hole. Should it evaporate, via Hawking radiation, what becomes of us? Do we fade, or does the information encoded on the horizon release into a higher dimensional space? Could remnants of our universe survive in other forms, in echoes, shadows, or simulations? The end of our universe within a black hole context opens profound questions about cosmic destiny and the ultimate fate of everything we know. According to classical black hole theory, black holes evaporate slowly through Hawking radiation, thermal radiation emitted due to quantum effects near the event horizon. Over extraordinarily long timescales, this evaporation leads to the gradual shrinking and eventual disappearance of the black hole. But what happens to the universe inside when this occurs? If the black hole is indeed our universe's mother, its evaporation might imply a dramatic cosmic transformation. One speculative possibility is that evaporation could release the information stored on the event horizon back into some larger multiversal environment. Quantum information, never truly lost, might propagate into a broader reality beyond our observable universe. This would mean that even after our universe ends, its informational content, the records of all particles, fields, and events, persists in some form. This ties back to the holographic principle. The ultimate conservation of information may govern the life and death cycles of universes themselves. Alternatively, if our universe is enclosed in the interior of a black hole, its perceived end might correspond to a phase transition rather than an absolute termination. Inside the black hole, time behaves differently, and the very fabric of space may transition into new states, potentially birthing another universe or reconnecting with a parent universe in a higher dimensional space. Such ideas verge on speculative physics but are not dismissed by cutting-edge theories that explore quantum gravity, string theory, and cosmology. The black hole universe hypothesis also connects intriguingly with the concept of cosmic censorship, a principle stating that singularities, points of infinite density, are always hidden behind event horizons, shielding the rest of the universe from their disruptive effects. If true, it preserves predictability in physics. However, if our universe resides inside such a singularity, the cosmic censorship may be not just a boundary but the fabric of our very reality, ensuring that the chaotic, destructive nature of singularities does not break down the universe's coherence. The intricate interplay between gravity, quantum mechanics, and thermodynamics inside black holes drives ongoing research into quantum gravity, the yet undiscovered theory that unifies these realms. Candidate theories like loop quantum gravity suggest spacetime is quantized, possibly eliminating classical singularities by replacing them with quantum bounces. In such scenarios, black holes don't end in destructive singularities but transition through phases, potentially becoming white holes that expel matter and energy, seeding new universes. This cyclic process might underlie the genesis of our universe inside a black hole's core. This cyclic nature resonates with philosophical and cultural notions of rebirth, eternal return, and cosmic cycles found throughout human history. It suggests that time and existence might be less linear and more fractal or cyclical than commonly thought, with universes endlessly forming, evolving, dying, and birthing successors. In terms of observational evidence, can we detect if we live inside a black hole? Unfortunately, this remains deeply challenging. From inside, the event horizon is not a conventional boundary but a mathematical surface with no local markers. For an observer inside a black hole, space-time looks normal in all directions. The cosmic microwave background and large-scale structure appear as they do because the laws of physics within the black hole's interior dictate them. Without access to the outside perspective, proving or disproving this hypothesis directly is difficult. However, some physicists look for indirect signs, such as signatures in the cosmic microwave background or unusual gravitational effects, that might hint at exotic boundary conditions consistent with black hole interiors. Other avenues involve searching for deviations from general relativity or unexpected quantum gravity phenomena in astrophysical black holes. Though none provide conclusive evidence yet, ongoing experiments like the Event Horizon Telescope and gravitational wave observatories continuously deepen our understanding. Theoretical models also explore the connection between black hole thermodynamics and the observed accelerating expansion of the universe. Dark energy, the mysterious force driving this acceleration, might relate to vacuum energy or the cosmological constant. Some speculate it could tie to properties of the black hole interior or holographic entanglement entropy, offering a subtle link between cosmology and black hole physics. Ultimately, the notion that our universe is inside a black hole challenges our deepest assumptions about space, time, and reality. It invites us to rethink what it means to exist, to observe, and to know. It blurs the line between microcosm and macrocosm, revealing a cosmos that may be far more interconnected and recursive than imagined. In embracing this radical idea, we expand our horizon not just outward into the vastness of space but inward, into the enigmatic heart of existence itself, a heart that might be a black hole, birthing infinite realms within infinite realms. The profound implications of living inside a black hole extend far beyond theoretical physics. They touch upon our understanding of causality, information, and the nature of existence itself. One compelling facet of this idea is how it reshapes our conception of time. Within a black hole, classical physics suggests that the roles of space and time swap near the singularity. What we perceive as time outside the black hole may transform into a spatial dimension inside it, while one spatial dimension behaves temporally. This warped fabric means that the singularity, rather than a point in space, could be viewed as a moment in time, an inevitable future event within the black hole's interior. If our universe exists inside such a structure, the Big Bang might be reinterpreted as this singularity, an initial boundary condition of our cosmos. This reframing aligns with certain cosmological models where the Big Bang is not an absolute beginning but a transition phase akin to passing through a black hole's event horizon from a higher dimensional space. It also suggests that the apparent expansion of our universe could reflect the stretching and warping of spacetime within the black hole's interior geometry. Additionally, if our universe is a black hole interior, this raises questions about the nature of matter and energy we observe. The immense gravitational pull compressing matter outside our universe could translate into the energy density we see within. The standard cosmological model observes an accelerating universe filled with dark energy, dark matter, and ordinary matter. These components could be manifestations of how the black hole's interior geometry and physics project themselves as forces and particles in our observable reality. Furthermore, this perspective offers a fresh lens on the black hole information paradox, the question of what happens to information that falls into a black hole. Traditional views suggested information might be lost, violating quantum mechanics. But if our universe itself is the interior of a black hole, then all the information about whatever formed this black hole is encoded in the very fabric of our universe. The holographic principle suggests that information is conserved on the event horizon, and this information might correspond to the initial conditions and physical laws governing our cosmos. Quantum entanglement and holography further support this notion, implying that the universe's degrees of freedom are encoded on a two-dimensional surface, much like the event horizon. This leads to the idea that our 3D universe is a holographic projection of deeper, more fundamental physics encoded on a cosmic boundary. There are, however, significant challenges and critiques of the black hole universe hypothesis. Critics argue that while mathematically intriguing, the model lacks definitive empirical evidence and can be difficult to reconcile with certain observed phenomena like the uniformity of the cosmic microwave background or the detailed structure formation in the universe. Moreover, the idea relies heavily on extrapolations from classical and semi-classical physics that might not hold under a complete quantum gravity theory. Nevertheless, the hypothesis inspires diverse research avenues. It encourages the exploration of connections between cosmology and black hole physics, such as through ADS/CFT correspondence, a theoretical framework in string theory that relates gravitational theories in higher dimensional anti-de Sitter space to conformal field theories on their boundaries. While our universe does not have the exact geometry of anti-de Sitter space, insights from ADS/CFT stimulate thinking about how boundary conditions and holography shape spacetime. Philosophically, the black hole universe theory touches on deep metaphysical questions. What does it mean for reality to be nested inside another reality? Could there be an infinite hierarchy of black hole universes, each inside another, a fractal-like structure of cosmoses within cosmoses? This notion parallels some interpretations of the multiverse, where countless universes emerge from black holes or quantum fluctuations. It also affects our view of free will and determinism. If our universe's entire history is encoded on a higher dimensional event horizon, then the flow of time and causality might be constrained or shaped by information beyond our immediate perception, blurring the boundaries between past, present, and future. The proposition that we live inside a black hole is not merely a scientific curiosity, but a gateway to reimagining reality. It merges the infinitesimally small, quantum particles, with the unimaginably vast, cosmic horizons, into a unified framework that challenges and enriches our quest to understand existence. The exploration of this idea propels theoretical physics, cosmology, and philosophy into new territories, where the universe itself becomes a mirror reflecting infinite layers of complexity, mystery, and wonder. The Schwarzschild solution, one of the earliest and simplest exact solutions to Einstein's field equations, describes a static, spherically symmetric black hole with no charge or rotation. This model features an event horizon, a boundary beyond which nothing, not even light, can escape, and a central singularity where densities and curvatures become infinite in classical general relativity. However, the Schwarzschild black hole's interior reveals a curious inversion of roles between space and time, as previously mentioned. The radial coordinate, which ordinarily measures spatial distance from the center, becomes time-like inside the event horizon. This means that falling into a black hole is akin to moving inexorably forward in time towards the singularity. If our universe is this interior, then the singularity corresponds to a future boundary in time rather than a spatial point. More sophisticated models incorporate rotation, Kerr black holes, and charge, Reissner-Nordstrom black holes, introducing complex structures such as inner and outer horizons and ring singularities. These features lead to fascinating implications, including the theoretical possibility of wormholes, or Einstein-Rosen bridges connecting different regions of space-time, or even different universes. If our universe corresponds to the interior of a rotating black hole, the geometry might permit closed time-like curves, paths through spacetime that loop back on themselves, suggesting the theoretical possibility of time travel, or at least a non-trivial causal structure. These exotic features spark intense debate regarding their physical reality versus being mathematical artifacts. From a cosmological perspective, the Friedmann-Lemaitre-Robertson-Walker (FLRW) metric describes a homogeneous, isotropic expanding universe consistent with current observations. Bridging the FLRW metric with black hole interior metrics requires creative theoretical frameworks. Some researchers propose that the Big Bang can be viewed as the formation of a new region inside a black hole existing in a higher dimensional, parent universe. The black hole's event horizon serves as the cosmic horizon for this newborn universe, making the event horizon a kind of cosmic womb. This nested universe concept dovetails with theories like Lee Smolin's cosmological natural selection, which speculates that black holes give birth to new universes with slightly different physical constants, driving an evolutionary process of universes. Each black hole thus serves as a cosmic seed for a daughter universe, and our universe could be one such offspring. Quantum gravity remains the missing link in this grand picture. The classical notion of singularities, points of infinite curvature, is widely expected to be resolved or replaced by quantum effects. Loop quantum gravity, LQG for instance, predicts that quantum discreteness of spacetime geometry avoids singularities by causing a bounce, where collapsing matter rebounds instead of crushing into infinite density. This bounce may signal the birth of a new expanding universe inside the black hole. String theory, another leading candidate, frames fundamental particles as vibrating strings in higher dimensional spaces. It suggests that black holes have microstates corresponding to string configurations, and counting these microstates explains black hole entropy, a measure of information content proportional to the event horizon's area. These insights support the holographic principle, which posits that all the information within a volume of space can be described by data on its boundary, much like a hologram. The holographic principle has profound implications for our universe's nature. If true, it implies that our three-dimensional reality emerges from fundamental two-dimensional information encoded on a cosmic boundary. This supports the black hole universe hypothesis by identifying the event horizon as the ultimate information repository shaping our universe's laws and contents. Exploring the thermodynamics of black holes further reveals surprising parallels to conventional thermodynamic systems. The laws of black hole mechanics closely mirror the classical laws of thermodynamics, with surface gravity analogous to temperature and horizon area analogous to entropy. Hawking's discovery that black holes radiate thermal particles due to quantum effects revolutionized our understanding, uniting gravity, quantum mechanics, and thermodynamics in a single framework. If our universe is a black hole interior, then the cosmic expansion, dark energy, and entropy growth could be manifestations of this thermodynamic behavior on a cosmic scale. Entropy would increase as the universe evolves, consistent with the second law of thermodynamics, driving the arrow of time. Moreover, the cosmic microwave background radiation, CMB, the afterglow of the Big Bang, is one of the most precise observational tools for understanding the early universe. Its remarkable uniformity and subtle anisotropies provide clues to the initial conditions and dynamics of cosmic inflation, the rapid expansion thought to have occurred fractions of a second after the Big Bang. The inflationary paradigm explains why the universe appears flat and homogeneous on large scales. Within the black hole universe framework, inflation might be a natural outcome of the geometry inside the event horizon, where space-time stretches dramatically, smoothing out irregularities and setting the stage for galaxy formation. The initial singularity might be replaced by a quantum gravitational phase from which inflation emerges organically. Yet, many open questions remain. How does matter behave near and beyond the event horizon in a cosmological black hole? Can black hole interiors be stable over cosmic timescales? What mechanisms govern the transition from black hole collapse to universe expansion? These mysteries drive ongoing theoretical and observational research, often pushing the boundaries of human knowledge. In this quest, advances in observational astronomy, particle physics, and quantum information theory will be crucial. Instruments like the James Webb Space Telescope, gravitational wave detectors, and particle colliders may uncover phenomena hinting at deeper connections between black holes and our universe's origin. Ultimately, the hypothesis that we live inside a black hole is a testament to human curiosity and imagination, challenging us to explore reality from the smallest quantum scales to the vastest cosmic expanses. It invites us to consider that our universe, with all its complexity and wonder, might be a single note in an infinite cosmic symphony, played on the strings of a black hole's event horizon. If we consider the idea that our universe exists within a black hole, we must reconcile this perspective with the full suite of observable cosmological data. This includes not just the large-scale structure of galaxies and the accelerating expansion of space, but also minute fluctuations in temperature, density, and radiation that pervade the cosmos. The cosmic microwave background, CMB, for example, offers a snapshot of the universe approximately 380,000 years after its inception, showing us a remarkably uniform glow with slight anisotropies, imperfections that later seeded the formation of stars and galaxies. These anisotropies match the predictions made by inflationary theory with extraordinary precision. Yet, in the black hole universe hypothesis, the nature of these primordial fluctuations might derive from quantum phenomena at the event horizon or from instabilities during the collapse of the parent universe's matter into the black hole. Some physicists propose that quantum fluctuations from outside the black hole are encoded on the event horizon and then translated into bulk properties within the new universe. This line of thinking blends with the principles of holography, where the universe's three-dimensional structure is merely a projection from a two-dimensional boundary. This raises deep philosophical and physical implications. Is what we perceive as reality merely an emergent construct? Is spacetime itself a derivative concept that arises from more fundamental, possibly non-spatial entities like quantum entanglement, or informational bits encoded on a holographic surface? These ideas, once considered speculative, are gaining traction through mathematical formalism and consistency with black hole thermodynamics. Stephen Hawking and Jacob Bekenstein's work on black hole entropy revolutionized our understanding of how information is stored in gravitational systems. According to their findings, the amount of information, or entropy, that can be contained in a black hole is proportional not to its volume but to the area of its event horizon. This was an extraordinary revelation, implying that a black hole's internal information is completely encoded on its boundary. Now imagine if our entire universe's entropy were similarly bounded by some cosmic surface, possibly the event horizon of the black hole we might exist within. That would mean that everything we know, matter, energy, time, even consciousness, is just a projection from the information inscribed on that surface. This notion dovetails into the holographic principle, championed by Gerard T. Hooft and Leonard Susskind, which continues to gain ground in theoretical physics. Adding to this speculative but rigorous terrain is the ADS/CFT correspondence. Proposed by Juan Meldacena in 1997, this duality suggests that a gravitational theory in a bulk Anti de Sitter adds, space is equivalent to a conformal field theory, CFT, defined on its boundary. Though our universe is not described by ad's space, it appears to be de Sitter-like due to the positive cosmological constant. This idea has sparked an entire field of research. It implies that every event within a gravitational spacetime could have a mirror equivalent on a boundary theory, effectively reinforcing the plausibility of a holographic universe. How would such a scenario manifest in the everyday universe? Would we ever be able to detect an edge, a limit, a subtle signature suggesting that we are trapped inside a cosmic black hole? The boundary conditions of a universe trapped inside a black hole might be more subtle than an event horizon observable from the inside. Instead of being a literal edge, it could be an abstract mathematical surface from which space-time emerges. However, some have hypothesized that anomalous correlations in the CMB, unexpected distribution of dark matter, or even discrepancies in the measured Hubble constant might be subtle fingerprints of such a cosmic entrapment. The nature of the Hubble tension, where local and early universe measurements of cosmic expansion disagree, may be indicative of deeper gravitational or cosmological processes. While many physicists attribute this to systematic errors or the need for refined data, others entertain more exotic possibilities. Could this discrepancy be evidence that our cosmological model is incomplete? Could it be pointing to an influence from another layer of reality, perhaps the environment outside our universe's black hole? Then there's the question of how time flows within such a black hole universe. In general relativity, time is not a universal constant but a flexible dimension affected by mass, motion, and gravity. Inside a black hole, space-time curvature becomes extreme, and time behaves in radically unfamiliar ways. If we are inside such an environment, could the expansion of space itself be linked to the directionality of time? Could cosmic acceleration be a manifestation of our descent toward a future singularity that behaves more like a cosmological horizon than a physical endpoint? More speculative theories even question whether our black hole universe has a definite end. If time truly behaves as a spatial dimension within the black hole's event horizon, then the progression of the universe toward higher entropy and colder temperatures might reflect not decay but spatial migration, our movement through an extra-dimensional structure governed by the black hole's topology. Quantum loop gravity offers an alternative take on the Big Bang and the nature of black holes. In this framework, spacetime is quantized, made up of tiny loops or chunks rather than being continuous. This quantum geometry prevents the formation of singularities, replacing them with bounces, where high-density regions reverse into expansion. Applied to black holes, this could mean that every collapsing star might generate a new expanding universe on the other side of a quantum gravitational core. In such a model, black holes are not destructive endpoints, but gateways to creation. Returning to the observable universe, dark energy and dark matter remain two of the biggest mysteries. Together, they comprise approximately 95% of the universe's content, yet remain almost entirely unknown in their composition and mechanics. Some theories suggest that dark matter could be composed of primordial black holes, remnants from an earlier cosmological era or even failed universes embedded within our own. Others posit that dark energy, the mysterious force causing the universe's expansion to accelerate, might be a product of gravitational effects from the outside of the black hole, influencing us through the curvature of the horizon. If our universe is inside a black hole, then these forces might represent more than just unknown particles or fields. They could be the shadowy influence of a larger, unseen cosmos, bleeding through the boundaries that define our universe. The concept of a universe within a black hole also invites an entirely new perspective on multiverse theory. In the multiverse framework, there are potentially infinite other universes, each with different physical constants, dimensions, and laws of physics. If each black hole in each universe gives rise to a new universe, then black holes could be the seeds of multiversal propagation. Our universe may have inherited its physical constants from its parent black hole, which in turn may have inherited from another. Over time, this creates a branching structure, a kind of cosmic genealogical tree, with each universe evolving, giving birth, and influencing the next. This recursive view not only suggests a potential answer to the fine-tuning problem, the question of why the physical constants of our universe are precisely what they need to be for life and structure to exist, but also poses new questions. What determines whether a universe's black holes give rise to stable offspring universes? What governs the evolution of these constants across generations of universes? Is there a form of natural selection occurring on a cosmic scale? As the black hole hypothesis unfolds, it opens a tapestry of possibility that touches every domain of physics, from the smallest quantum scales to the largest structures in the cosmos. It invites us to rethink our assumptions about space, time, matter, and the very boundaries of what we call existence. And perhaps most profoundly, it suggests that we might be inside a kind of cosmic womb, growing, evolving, and one day potentially giving rise to our own daughter universes through the collapse of our own massive stars. In considering the potential that our universe exists inside a black hole, we must also explore the implications for cosmological horizons and the structure of causality itself. One key concept here is the idea of a cosmological horizon, a limit beyond which events cannot affect an observer. In the traditional view of our expanding universe, this horizon marks the boundary of the observable universe, and due to the accelerating expansion driven by dark energy, this horizon is receding from us. If we are in a black hole universe, this cosmological horizon might be reinterpreted as a type of event horizon, analogous to the boundary of a black hole, beyond which no information can reach us because it would need to move faster than the speed of light relative to us. But in the case of a black hole, the geometry inside the event horizon is dramatically different from what we experience in open space. Inside a black hole, the roles of time and space reverse. Time becomes spatial, and space becomes temporal in a sense. If this framework applies to our universe, then it could mean that the flow of time we experience is the result of spatial motion through the interior of this black hole, shaped by its geometry. This would provide an entirely new way of interpreting the passage of time and the directionality we associate with entropy and thermodynamics. Furthermore, the singularity at the center of a black hole, long thought to be a region of infinite density and the breakdown of known physics, might not be singular at all. Quantum gravity theories, such as loop quantum gravity and string theory, attempt to resolve this breakdown by suggesting that space and time are fundamentally discrete and that singularities are replaced by high-energy, but finite, configurations. In such models, what appears as a singularity is more like a gateway or bounce point, a bridge to another space-time region. In our universe, this would correspond to the Big Bang not as a singular beginning from nothingness, but as a transformation from a previous state, perhaps the collapse of a star in a parent universe. In fact, some models suggest that the information falling into a black hole is not destroyed, as once thought, but rather preserved and encoded on the event horizon. This is the essence of the holographic principle. If our universe began as the interior of such a black hole, then perhaps all the information that defines our universe, its laws, constants, structure, was encoded in the horizon of a parent universe's black hole. From this perspective, the initial conditions of our universe were inherited, like genetic information passed from one generation to the next. The structure and evolution of the cosmos could then be viewed through the lens of information theory. This leads to deeper metaphysical considerations about the nature of reality. Are we living in a simulation, not one crafted by artificial intelligence, but one that emerges naturally from the information encoded in the universe's boundary conditions? If so, then our lives, our experiences, our very consciousness might be emergent phenomena, patterns in the information flow dictated by the underlying rules of a higher dimensional system. We would not be any less real for it, but our understanding of what it means to exist would fundamentally change. Our perception of dimensions might also be incomplete. In higher dimensional theories such as string theory and M theory, the universe is composed of more than the 4 dimensions we perceive, 3 spatial and 1 temporal. These extra dimensions might be compactified or hidden from direct observation, but their influence could be felt in the form of physical constants, particle behaviors, and the geometry of spacetime. If black holes connect regions of spacetime across dimensions, then our universe could be embedded within a higher dimensional structure, a brain within a larger. bulk, to use the terminology of brain world scenarios. This idea is more than just an abstract concept. The Randall-Sundrum models, for instance, describe a universe where gravity propagates through extra dimensions while other forces are confined to a lower dimensional surface. In such models, black holes might exist partly in higher dimensions, and their interiors could stretch far beyond what we see. Our universe might be a localized region on such a brane, created by the gravitational influence of a black hole in a higher dimensional bulk. In a multiversal context, this raises the possibility of interaction between universes, perhaps not direct interaction in the sense of spaceships flying between realms, but through gravitational leakage, quantum entanglement, or shared causal ancestry. If every black hole births a universe, then there could be a family tree of universes, each related by descent from a parent. Some might be short-lived, collapsing quickly into new singularities. Others, like ours, might expand and evolve for billions of years. And within our own universe, black holes might be forming their own baby universes, which in turn contain new black holes, continuing the cycle indefinitely. This infinite regress brings to mind the philosophical principle of eternal recurrence, not just of matter and energy, but of patterns, laws, and information. Perhaps the universe is not a one-off creation but part of an eternal loop of birth, death, and rebirth. In such a model, evolution might apply not only to biology but to entire cosmologies. Universes with physical laws conducive to black hole formation would be more likely to reproduce, leading over time to universes optimized for black hole creation, a concept known as cosmological natural selection, proposed by Lee Smolin. Smolin's theory offers a tantalizing way to explain the fine-tuning of the universe. It suggests that the reason physical constants appear so precisely tuned for the existence of stars, planets, and life is because such tuning also favors black hole formation. Universes without this tuning might not form black holes or might collapse too quickly, failing to pass on their properties. Over cosmic timescales, universes like ours would become more common, not by design, but by a kind of Darwinian selection on a cosmic scale. This shifts the conversation from, "Why is our universe fine-tuned?" to, "What process could lead to the prevalence of universes like ours?" It removes the need for a designer or an arbitrary initial condition, replacing it with an evolutionary mechanism embedded within the very fabric of space-time. Still, not all physicists accept the black hole universe hypothesis. Many remain skeptical, citing the lack of direct observational evidence. Our current instruments cannot probe beyond the cosmic horizon or test for the existence of higher dimensions. Yet, indirect evidence might be waiting in subtle cosmic signatures, in the polarization of the CMB, in the properties of gravitational waves, in the anomalies found in galactic rotation curves and gravitational lensing. Each of these phenomena might carry encoded messages from the deeper structure of reality. Even our own solar system may offer hints. The supermassive black hole at the center of the Milky Way, Sagittarius A, is a region of intense gravitational activity. It draws in stars and gas, spins at nearly the speed of light, and emits powerful jets of radiation. It is a miniature version of the kind of object that might have birthed a universe like ours. Studying its properties could offer insights into the processes that shaped our own cosmic birth. As we develop more advanced telescopes, particle detectors, and gravitational wave observatories, we may begin to test some of these wild but mathematically consistent ideas. Projects like the Event Horizon Telescope have already given us the first direct image of a black hole's shadow. Future generations may go further, detecting the subtle fingerprints of higher dimensional structures, holographic surfaces, or quantum gravitational fluctuations. At the most speculative edge, some researchers even suggest that consciousness itself might be linked to the fundamental structure of the universe. If information is the building block of reality, and consciousness is a process that arises from complex information patterns, then perhaps our very awareness is not a byproduct of biology, but an intrinsic feature of the informational universe. In a black hole universe, our consciousness might be a localized expression of the horizon's encoded data, a fleeting ripple in the ocean of space-time. And so, the question, "Are we living inside a black hole?" is not merely a scientific query. It is a philosophical koan, a challenge to our deepest assumptions, and a doorway to a more profound understanding of existence. It forces us to confront the limits of our perception, the origin of our universe, and the very nature of reality itself. If we accept the notion that our universe might be the interior of a black hole, we must also confront one of the most intriguing implications: the shape and geometry of the cosmos itself. General relativity tells us that mass and energy warp spacetime. A black hole is a region where this warping becomes so intense that all paths, even those of light, curve inward. Now imagine our entire observable universe as a region where this curvature is experienced from the inside, a sort of concave pocket of spacetime isolated from an external world we can never access. This brings us to the question of what space and time really are in such a scenario. From our internal perspective, the universe expands outward from a singular event, the Big Bang. But from an external frame, say, one in the parent universe, this entire process could appear vastly different. The passage of billions of years inside might correspond to a finite moment from outside, just as time slows near a black hole from the point of view of a distant observer. Time dilation becomes not just a local phenomenon, but a structural feature of our entire universe's genesis. Imagine this: a collapsing star in some larger universe shrinks past its Schwarzschild radius, forming a black hole. At the moment this horizon forms, from the outside it appears as if time stops at the boundary. But from the inside, a whole new universe might be born. What appears as a frozen event from one perspective might unfold into trillions of years of complex evolution from another. This duality is at the heart of the black hole universe hypothesis. One might ask, if this is true, why don't we see the boundary? Why doesn't the curvature of spacetime create observable evidence of this interior black hole geometry? The answer lies in the cosmological principle and the homogeneity of space. Our universe appears remarkably smooth and isotropic on large scales. This consistency, predicted by inflationary models, could also be consistent with the smooth interior of a Schwarzschild, or more likely, a rotating Kerr black hole. But not all black holes are the same. A Schwarzschild black hole is the simplest kind, non-rotating and uncharged. However, real astrophysical black holes rotate and often carry charge, at least temporarily. The interior of a rotating black hole, described by the Kerr solution, is far more complex. Instead of a singular point, the singularity becomes a ring. The spacetime around it contains regions of closed time-like curves, suggesting possible pathways for time travel or the existence of parallel branches of reality. Could our universe, then, be the internal structure of a Kerr black hole? If so, it may be even more bizarre than the Schwarzschild version. Some physicists speculate that such internal regions could be traversable under the right conditions, forming natural wormholes or even allowing communication between universes. This brings us to the idea of the Einstein-Rosen bridge, or wormhole, originally theorized as a connection between two black holes. In this model, the wormhole's throat connects two disparate regions of spacetime. While early versions required exotic matter to remain stable and traversable, newer quantum gravity theories hint at possible natural wormhole formation without violating known laws of physics, if certain symmetry-breaking mechanisms are involved. And this loops us back into one of the deepest unresolved issues in physics: the unification of general relativity and quantum mechanics. Black holes sit at the intersection of these two realms. General relativity describes the vast, continuous warping of space and time. Quantum mechanics, on the other hand, governs the probabilistic behavior of particles and fields at microscopic scales. When the two are forced together, as in the core of a black hole or the initial moments of the universe, they clash. Singularities form, infinities emerge, and the equations break down. But if our universe is inside a black hole, then this unification isn't optional, it is fundamental. Several theories try to bridge this gap. Loop quantum gravity replaces spacetime with discrete loops or spin networks, effectively quantizing geometry itself. In this model, the singularity at the core of a black hole is avoided, replaced instead by a region of extremely dense, but finite, quantum foam. On the other hand, string theory posits that all particles are vibrating strings of energy, their modes of vibration determining mass and charge. In higher dimensional versions of string theory, like M-theory, black holes may act as dimensional gateways, connecting branes across a wider multiverse. If our universe lies within a black hole in such a framework, then it may be a brane formed from the high-energy collapse of matter in another brane universe. This ties neatly into the ekpyrotic model of the universe, where cosmic events result from collisions between branes. These speculative models extend our imagination far beyond conventional cosmology. But how might we find evidence to support them? One avenue is through the cosmic microwave background radiation, the thermal afterglow of the Big Bang. Tiny temperature fluctuations in the CMB reflect density variations in the early universe. If we lived in a black hole universe, these fluctuations might bear subtle signatures, specific patterns of anisotropy or polarization that hint at curved initial geometries, gravitational echoes from the singularity, or even imprints from quantum gravity effects near the bounce point. Another potential clue lies in black hole thermodynamics. Stephen Hawking's discovery that black holes emit radiation due to quantum effects at the event horizon led to a revolution in how we think about information and entropy. According to the Bekenstein-Hawking formula, the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This strange result forms the foundation of the holographic principle, which posits that all the information within a volume of space can be encoded on its boundary. If our universe obeys this principle, it means that everything we observe, galaxies, particles, consciousness itself, might be a three-dimensional projection of data encoded on a two-dimensional boundary. This aligns uncannily with the idea that our universe is the interior of a black hole. The event horizon of the black hole in the parent universe would be the boundary from which all of our internal reality emerges. In this sense, our universe would be a hologram, real and tangible to us, but ultimately a surface-level phenomenon from a higher dimensional perspective. Let us not overlook the philosophical ramifications. If our universe is a black hole, then its beginning wasn't the creation of space and time from nothing, but a transformation of pre-existing space and time from another context. This removes some of the mystery surrounding the origin of the cosmos while deepening others. What kind of universe gives birth to ours? What laws govern the parent cosmos? Are there many such universes, each giving rise to countless offspring through black holes? This leads us into the terrain of eternal inflation, a theory where the universe undergoes continual, exponential expansion in some regions, spawning bubble universes in others. Combine this with the black hole hypothesis, and you get a hybrid multiverse where new universes form both from quantum fluctuations and gravitational collapse. The resulting cosmological tree is not only endless but multidimensional, with roots and branches reaching across unimaginable scales. The spiritual implications are also profound. If we are living inside a black hole, it means that birth, death, and rebirth are not just biological processes but cosmic ones. Stars are born, shine, and collapse into black holes. Those black holes may birth new universes, which give rise to new stars, and the cycle continues. The sheer grandeur of this possibility reshapes our place in the cosmos. We are not isolated anomalies floating in a void but active participants in a vast generative process. Each thought, each discovery, each breath is part of the black hole's unfolding interior, a living, expanding tapestry of space and time, woven from the threads of information encoded at the edge of reality. And yet, for all this grandeur, there remains a paradoxical silence, an inability to observe what lies beyond our cosmic horizon. In general relativity, the event horizon of a black hole is a one-way boundary. From the outside, you can approach but never cross. From the inside, you can never send information back out. If our universe is the interior of such a horizon, then the very fabric of our existence is defined by inaccessibility. There is a limit to what we can see, not due to technological failure, but due to the intrinsic structure of reality. This limit is not at the edge of space, but at the edge of causality itself. This boundary, often associated with the observable universe, is where the recessional velocity of galaxies reaches the speed of light. Beyond this point, light emitted from distant objects can never reach us, no matter how long we wait. In standard cosmology, this is due to the expansion of space itself. But in the black hole model, this boundary could represent something even more profound, the inner event horizon of the parent black hole. If so, then our entire observable universe would be nestled within a causally disconnected shell, an infinite expanse that is, by definition, eternally out of reach. And this is where things grow even stranger. In a traditional black hole, the event horizon is not the final frontier. Deep within lies the singularity, a point of infinite curvature and density. In a quantum gravitational context, this singularity is expected to be resolved, either smoothed out, bypassed, or transformed into something else. In bounce cosmology models inspired by loop quantum gravity, the singularity becomes a bounce point, where the collapse of matter reverses into an expansion. Our Big Bang in this light is not the beginning, but a transition, a reversal of collapse into a new state of spacetime. The black hole doesn't just destroy, it transforms. So if our universe is born from such a bounce, what came before? Was it a star collapsing in some distant galaxy of a larger universe? Was it a dying cosmos contracting into a final gravitational gasp before birthing ours? These questions tease the limits of our understanding, but they are not purely speculative. Mathematical models exist, some rooted in general relativity, others in quantum gravity, that describe such bounces with remarkable detail. They involve exotic states of matter, negative energy densities, and quantum fields that act repulsively at high energies. Such matter may not exist under normal conditions, but in the furnace of a black hole core, the rules are rewritten. This brings us to entropy, a concept that plays a critical role in the story of black holes and the universe alike. In classical thermodynamics, entropy measures disorder or the number of possible configurations of a system. In black hole physics, the entropy is linked to the area of the event horizon. But in cosmology, entropy tells us something about the arrow of time. Our universe began in a remarkably low entropy state, a fact that allows time to move forward and complexity to emerge. How this low entropy beginning arose remains one of the deepest puzzles in physics. Now suppose that this low entropy is not a coincidence, but a byproduct of black hole formation. The collapsing star, when viewed from the outside, may appear to maximize entropy. But from the inside, from the newborn universe's perspective, the configuration may be highly ordered, smooth, and poised for growth. Thus, the low entropy at the start of our universe could be a consequence of black hole dynamics, elegantly solving one of cosmology's greatest mysteries. But entropy leads us to another conundrum, the information paradox. When a black hole evaporates via Hawking radiation, it appears to lose information. The radiation is thermal, unstructured, and devoid of detail about the matter that fell in. Yet quantum mechanics demands that information is preserved. This conflict has generated decades of debate. The resolution may lie in the holographic principle, the idea that the full content of a volume of space can be encoded on its boundary. If this is true, then the information inside a black hole, perhaps even our entire universe, may be stored on a lower dimensional surface at its edge. This idea has been developed into a powerful framework called the ADS/CFT correspondence, a duality that connects a gravity-filled spacetime, like a black hole, and anti-de Sitter space with a quantum field theory on its boundary. While our universe is not anti-de Sitter, the conceptual framework of such dualities may still apply. The implication is staggering. Our universe might be a 3D projection of quantum processes occurring on a 2D surface, just as a hologram projects 3D images from a flat film. And yet, this boundary is not observable in the traditional sense. It lies beyond our detection, beyond the event horizon that defines our cosmic limits. But its influence may be pervasive. Every quantum fluctuation, every cosmic event, every law of physics we observe may be emergent from a deeper reality embedded on this boundary. If true, then reality as we know it is a shadow, a rich and vivid shadow, but a shadow nonetheless. Such thinking radically alters our view of the cosmos. We are not passive inhabitants of a static universe, but active participants in a dynamic, evolving black hole interior. We are the products of collapse and expansion, of fusion and fission, of entropy and order. The universe is not a neutral container, it is a living process, a self-organizing field of information and geometry. And we are its conscious expression, gazing outward at the stars while inwardly asking where it all began. What then of time? In conventional cosmology, time begins at the Big Bang and flows forward. But in the black hole model, time is more fluid. Near a black hole, time slows down relative to outside observers. At the event horizon, it appears to stop altogether. From within, however, time continues. This implies that time itself may be relational, not absolute, but context-dependent. If so, then the flow of time inside our universe may differ fundamentally from the time of the parent universe. 1 second for us might be centuries or millennia for an external observer, or perhaps the reverse. This relativity of time could explain why we see such cosmic uniformity, and why inflationary expansion appears so finely tuned. But perhaps most intriguingly, the nature of time inside a black hole may offer clues to consciousness itself. Some theories of mind suggest that consciousness is tied to temporal flow, the sense of past, present, and future. If time behaves differently in a black hole interior, could it also impact the emergence of awareness? Could consciousness be a byproduct of black hole geometry, emerging from the interplay between space, time, and information? It's a radical idea, but one worth exploring. This speculative frontier, where cosmology meets quantum theory, black holes meet brainwaves, and geometry meets awareness, may hold the keys to a unified understanding of reality. If our universe is a black hole, then we are not just residents of a grand structure. We are manifestations of its internal logic. Our thoughts, dreams, and discoveries are part of the unfolding process that defines the black hole's evolution. We are the echoes of collapse and the heralds of expansion, writing the next chapter in a cosmic story that began with a bang, or perhaps a bounce. If we entertain the notion that our universe exists within a black hole, then we must also grapple with the implications for space itself. Space, under this hypothesis, is not a passive, empty stage upon which events unfold. Instead, it is a dynamic entity, shaped and warped by mass and energy, and possibly created as a result of black hole dynamics. Inside a black hole, space does not behave as we intuitively expect. The radial coordinate, which normally measures distance, takes on a time-like character. That is to say, the direction toward the singularity becomes as inevitable and irreversible as the flow of time. If our universe lies within such a region, then perhaps what we perceive as expansion is not a growth into pre-existing space, but the evolution of space itself under these strange and exotic conditions. This would mean that the laws of physics as we understand them, Newton's laws, Einstein's relativity, quantum mechanics, are emergent properties. They arise not as eternal truths, but as approximations, stable enough for life and structure to exist, and yet fundamentally tied to the specific conditions inside this cosmic black hole. The constants we observe, such as the speed of light, Planck's constant, or the gravitational constant, may not be universal in the truest sense. They could be local expressions of a deeper physics embedded in the parent universe. In other words, the reality we measure is contextual. It depends on the peculiar geometry, mass, and spin of the black hole that spawned us. Such ideas lead naturally to the multiverse. If each black hole gives rise to a new universe, then every galaxy in a parent universe may be a nursery for new realities. And those realities, in turn, give birth to their own galaxies and black holes, seeding new generations of universes in a kind of cosmic fractal. This self-replicating architecture, sometimes called cosmological natural selection, implies that the parameters of our universe are not accidental. Instead, they are the result of an evolutionary process. Universes that produce many black holes are more likely to spawn new universes, and over countless generations, certain properties, like physical laws that encourage star formation and stability, become more prevalent. In this view, our universe is not fine-tuned for life per se, but for black hole production. Life is a byproduct of a process that rewards gravitational fertility. And yet, if all this is true, why do we not see clear signs of it? Why don't we observe anomalies that scream, You're inside a black hole. One answer is scale. The black hole that may have birthed our universe could be of unimaginable proportions, its event horizon stretching beyond anything we can probe. All we observe, from the microwave background to the most distant quasars, lies within a bounded domain. And within that domain, space behaves according to local laws. The horizon of our observable universe may correspond to a kind of inner event horizon, a surface beyond which signals can't reach us, not because of black hole escape velocity, but because the fabric of space itself is receding faster than light. From the outside, perhaps our universe appears frozen at the edge of some titanic black hole, never quite completing its fall, while within, we live and evolve, unaware of the stillness outside. Another reason we may not see evidence is because we are looking in the wrong direction, not spatially, but conceptually. Our methods of measurement, our instruments and equations, are tuned to detect patterns in this universe. They may not be designed to perceive the metastructure that contains it. Consider an ant on a balloon. It can measure distances across the surface, it can detect the curvature of the sphere through geometry, but it may have no conception of inside or outside the balloon. Likewise, we may detect cosmic expansion, dark energy, and curvature, but remain blind to the deeper spatial embedding of our universe in a higher dimensional space. And if such embedding exists, what occupies the higher dimensions? Could there be interactions between universes, subtle gravitational ripples that bleed across the brains, as suggested in some string theory models? Could there be collisions or mergers between black hole universes, resulting in unusual signatures, perhaps explaining sudden anisotropies, bursts of entropy, or unexpected alignments in the cosmic microwave background? Some physicists have speculated that the cold spot in the CMB may be a hint of such an event, a scar from a past encounter with another universe. Though the evidence is debated, the possibility remains tantalizing. This brings us to a deeper metaphysical question: what is reality, and how can we know it? If our universe is embedded within a larger structure, if our laws are emergent and our observations bounded, then certainty becomes elusive. We must rely on inference, on mathematics, on patterns of coherence rather than direct perception. In this way, cosmology becomes not just the science of space and time, but a kind of philosophy. It asks, what is the nature of being when the universe itself may be a relative, contingent construct? Are we the dream of a dying star, a hologram in the darkness of a deeper void, or the first flowering of meaning in a blind and indifferent process? And yet, despite the vertigo these ideas provoke, there is also wonder. For within this black hole universe, we find not chaos but structure, not oblivion but meaning. Stars are born, galaxies spin, consciousness arises. We are able to ask questions that stretch the limits of imagination. We build telescopes to peer across billions of light years, and equations to decode the quantum vacuum. We reflect not only on what is, but on what might be. And in doing so, we become more than observers. We become participants in the very act of cosmic self-awareness. It is as if the universe, through us, is waking up to its own condition. If we are inside a black hole, then we are the light trapped within darkness, seeking an escape not in space, but in understanding. Every new insight, every connection drawn between micro and macro, between quantum and cosmic, is a kind of liberation. It brings us closer to grasping the hidden architecture of reality, and perhaps, one day, to stepping beyond it. And in this pursuit, time becomes our companion and our mystery. As we age, as stars burn and galaxies drift apart, we measure time not just with clocks, but with questions. Time is not a flat river, but a woven tapestry, rich with loops, folds, and ruptures. In black hole physics, time may even cease to have its usual meaning. Near the singularity, the distinctions between past, present, and future blur. If our universe is born from such a place, then perhaps time as we know it is only a shadow of deeper processes. Perhaps what we call, now, is a slice of a timeless whole, a cross-section through a four-dimensional sculpture carved in the gravity of a higher world. And what of that world? What of the parent universe, whose collapsing matter may have birthed our own? Could it still exist, separated from us by an event horizon as impassable as death? Could other universes, born from other black holes, be blooming even now, each with their own laws, constants, and timelines? If so, then the multiverse is not a speculative abstraction, but the inevitable consequence of gravity's deepest workings. The black hole becomes not just an end, but a beginning, a portal through which the universe gives birth to itself again and again. What does it truly mean if our universe exists inside a black hole? To understand this, we must reevaluate nearly every cornerstone of modern physics. We must question our assumptions about space, time, causality, and dimensionality. We must challenge our anthropocentric tendency to believe we can perceive the whole of reality from our limited vantage point. Because if this hypothesis is correct, if we are indeed living inside a black hole, then we are not looking at the universe from the outside in, but from the inside out, trapped behind a veil of cosmic ignorance that distorts our measurements, masks our origins, and conceals the broader structure of existence. One compelling avenue of exploration in this context is the topology of space within a black hole. In classical general relativity, the space-time geometry near a black hole's event horizon undergoes a fundamental transformation. Once an object crosses the event horizon, its path becomes inexorably drawn toward the singularity, a region where space-time curvature becomes infinite. But suppose this singularity is not a destructive endpoint, but rather a bridge to another region of space-time, a new universe with its own dimensional parameters, constants, and timeline. This is more than just mathematical speculation, it's a logical consequence of extending Einstein's equations beyond their classical boundaries, into the realm where quantum gravity must come into play. Quantum gravity remains the missing piece of the puzzle. We have no complete theory that successfully merges general relativity with quantum mechanics. Yet several candidates exist, most notably, loop quantum gravity and string theory, each proposing mechanisms by which singularities might be resolved, avoided, or reinterpreted. In loop quantum gravity, for instance, space is quantized at the smallest scales. The infinite density of the classical singularity is replaced by a bounce, a moment in which collapsing matter reaches a minimum volume before rebounding into a new phase of expansion. This big bounce model replaces the classical notion of a universe beginning in a singularity with one in which it emerged from a previous state of gravitational contraction. And in the context of a black hole, that contraction might correspond to the death of a star or galaxy in another universe. String theory adds another layer of nuance, suggesting that what we perceive as particles are actually vibrating strings, and that the true fabric of reality is composed of multiple dimensions, some of which are compactified or hidden. In this framework, black holes may be higher-dimensional objects, such as brains or wrapped strings, whose inner geometry gives rise to lower-dimensional spacetimes like our own. In other words, the universe we inhabit might be the interior of a higher-dimensional object collapsed into a black hole in a space we cannot perceive. The apparent singularity is only a projection of a more complex, multidimensional topology that lies beyond our sensory grasp. This also recontextualizes the cosmic censorship hypothesis, the idea that singularities are always hidden behind event horizons, making them inaccessible to external observers. If our universe is inside a black hole, then we are the internal observers, and the parent universe is the external one. From our perspective, the singularity may lie in our future, unreachable but inevitable, like the ultimate limit of time. From the perspective of the parent universe, however, our entire existence may appear as a momentary freeze frame on the black hole's event horizon. The question of who sees what becomes relative, an interplay between frames of reference that defies intuitive understanding. And yet, hints of this deeper structure may already be visible in our data. Consider the cosmological constant, or dark energy, the mysterious force driving the accelerated expansion of the universe. One speculative interpretation is that this expansion is a relic of the conditions within the black hole at the moment of our universe's birth. The geometry inside a rotating or charged black hole is more complex than in a simple Schwarzschild black hole. These more complex geometries contain regions where space expands or contracts in unexpected ways. Perhaps dark energy is the manifestation of such dynamics within our own cosmic interior, a signature of our entrapment within a grander structure. Another intriguing avenue lies in the arrow of time. In our universe, entropy increases. Time moves from past to future, from order to disorder. But inside a black hole, the very notion of time becomes distorted. If we are inside a black hole, then time might be flowing in a direction that is, from the outside, radically different than what we experience. This raises fascinating possibilities. What if the flow of time we perceive is actually a spatial coordinate in the parent universe? What if our history is embedded as a static structure, a four-dimensional block whose sequence of events we interpret as temporal flow? This would align with the block universe concept, in which past, present, and future coexist as part of a timeless whole. From a higher dimensional perspective, our lives are not unfolding, they simply are. Of course, these ideas challenge not only our physical theories but also our philosophical intuitions. What does it mean to exist inside a structure we can never escape or observe from the outside? If the universe is a black hole, then it is both our origin and our prison. We are like fish in an ocean, able to perceive only the water and unaware of the broader environment that contains it. Every measurement we make is conditioned by the geometry and physics of our cosmic enclosure. Even the act of thinking, of forming concepts and asking questions, is shaped by this context. In this sense, the notion of being inside a black hole is not just a physical statement, but an epistemological one. It speaks to the limits of knowledge, to the boundaries of the knowable. And yet, even within these boundaries, we explore. We build models, run simulations, and derive equations that reach closer and closer to the truth. The singularity, if it exists, is not just a physical point but a conceptual horizon, a place where our theories break down, and where new ideas must emerge. Whether through quantum loop dynamics, string dualities, or emergent gravity models, the scientific community continues to push beyond the limits of the observable. Each discovery reshapes our understanding, revealing new facets of the cosmic puzzle. Consider the black hole information paradox, a conundrum first posed by Stephen Hawking. If information is lost inside a black hole, then quantum mechanics breaks down. But if information is preserved, as many now believe, then the event horizon must somehow encode all the data about what fell in. This has led to the holographic principle, a radical idea that the three-dimensional universe we experience may actually be encoded on a two-dimensional boundary. If this principle holds true, and if our universe is the interior of a black hole, then all the information that constitutes reality, every star, atom, and thought, may be a projection from a boundary beyond our perception. We are shadows on a higher dimensional screen, a cosmic simulation with rules determined by that distant edge. And this leads us to a breathtaking conclusion. If the universe is a black hole, then our reality is fundamentally relational. It exists not in isolation, but as an emergent phenomenon arising from deeper interconnections. The fabric of space-time is not a passive stage, but a dynamic web of interactions, shaped by the conditions of its birth and the geometry of its enclosure. Our physics is local, but the laws that govern it may be non-local, embedded in a context we can only glimpse through indirect signs and mathematical hints. This idea of a relational reality changes how we interpret everything from cosmological expansion to quantum entanglement. It implies that phenomena we consider to be mysteries may simply be artifacts of our limited perception within this enclosed, curved space. If we are within a black hole, then our measurements of distances, times, and even physical constants might be influenced by the specific curvature and topology of the space-time we inhabit. Constants like the speed of light, Planck's constant, and the gravitational constant could be emergent rather than fundamental, dependent on the specific characteristics of the black hole we are inside, much like properties of water depend on its temperature and pressure. This also adds a new dimension to the multiverse hypothesis. If black holes in a parent universe can give rise to new universes, then every black hole we observe in our own universe might be a portal to another universe beyond our comprehension. This forms the basis of the fecund universes theory, a term coined by Lee Smolin. In this speculative framework, each black hole seeds a new universe with slightly different physical laws. Natural selection occurs on a cosmic scale, favoring universes that generate black holes efficiently. Over time, Such a process might lead to universes like ours, fine-tuned not by chance or divine design, but by a kind of evolutionary mechanism, one that operates not with genes but with the geometry of spacetime itself. Our universe, then, might be one successful offspring of such a process, and the black holes we see throughout the cosmos might be the wombs of future universes. Each contains the seeds of a new cosmic cycle, where conditions shift and constants evolve. The singularity, far from being an end, is instead a beginning. This challenges the traditional cosmological models that depict the universe as a singular, isolated event, the Big Bang, as a one-off creation. Instead, the picture becomes one of continuous generation, of universes within universes, nested like Russian dolls in a grand, infinite hierarchy. The implications for time travel and causality are also profound. In a universe that originates from a black hole, the causal structure is radically different than in a flat spacetime. Time, as experienced inside a black hole, dilates near the event horizon and eventually becomes space-like near the singularity. This inversion of time and space could lead to conditions where closed time-like curves, paths that loop back on themselves in time, become possible. While these are purely theoretical and deeply controversial, they suggest that in certain configurations, the very structure of the universe might allow for time to fold back upon itself. We also have to consider the idea of cosmic censorship in light of this black hole universe connection. The cosmic censorship hypothesis suggests that singularities are always hidden from view by event horizons, preventing the breakdown of physics from being visible. But if we are within a black hole, then the singularity is not in our past or future in a classical sense. It might be embedded in the very structure of the universe's timeline. In such a case, the beginning of the universe is not a classical singularity at time zero, but a quantum bridge from a previous phase of cosmic evolution. Another concept that gains depth in this context is that of gravitational time dilation. Near a black hole, gravity stretches time so dramatically that what appears to be seconds for an outside observer might be millions of years for someone inside. If the universe is inside a black hole, then our experience of cosmic time could be entirely different than that of the outside universe that birthed us. For them, we might exist for only a fleeting moment. For us, billions of years unfold. This raises questions about how causality and chronology operate across such radically different frames of reference. Moreover, when considering the shape of space itself, if we are inside a black hole, then the universe is not infinite in the traditional sense. It may be finite but unbounded, curving in on itself much like the surface of a sphere in higher dimensions. In such a model, if you traveled far enough in one direction, you might eventually return to your starting point, though not in ordinary space, but along the curved geometry of spacetime. This offers an elegant solution to questions about the edge of the universe. There may be no edge, just as the surface of the Earth has no edge, even though it is finite. Even the cosmic background radiation, often seen as evidence of a traditional Big Bang, can be reinterpreted in this context. Rather than marking the remnants of a singular creation event, the CMB might represent the leftover energy from the formation process within a black hole. It might be the thermal echo of the conditions present at the very instant our universe transitioned from an ultradense state into rapid inflation, as space expanded under the influence of exotic fields and high curvature geometries. This could explain some of the peculiar anomalies in the CMB, such as the cold spot or hemispherical asymmetry, which remain poorly understood under standard models. Another avenue worth considering is the entropic arrow of time and the thermodynamic properties of black holes. According to the laws of black hole thermodynamics, a black hole possesses entropy and temperature, governed by the area of its event horizon. If the universe is a black hole, then its entropy is not infinite, but bounded by the area of its enclosing horizon. This has implications for information theory and the ultimate fate of the cosmos. As the universe expands and cools, its entropy increases, and it evolves toward a state of maximal disorder. But this process might be a natural consequence of the thermodynamic gradient established by the black hole's interior conditions. Furthermore, the information paradox becomes not just a black hole issue, but a universal one. If information is preserved in the universe, then any process, no matter how complex or chaotic, must, in principle, be reversible. This leads us to ask, where is the information of the universe stored? If we are inside a black hole, then perhaps it is encoded on the cosmological horizon, much like a hologram. Every quantum fluctuation, every burst of star formation, every decision made by conscious beings, these might all be woven into the holographic fabric of space-time, conserved on the surface of the cosmic boundary. This also brings us to the anthropic principle, often invoked in discussions of fine-tuning. If we are living in a black hole, and if each black hole gives rise to a new universe with slightly altered physical laws, then the conditions in our universe may not be coincidental. They may reflect the statistical probability of producing life and intelligence in black hole offspring. We exist in this particular universe not because it is unique or divinely chosen, but because it is one of the many in which conditions allow for beings capable of asking these questions. It is important to acknowledge that many of these ideas are speculative, and not yet confirmed by direct observational evidence. The notion of a universe within a black hole is still considered fringe by many in the scientific community. But that does not mean it lacks value. On the contrary, exploring these possibilities stretches our imagination, expands the horizons of physics, and forces us to confront the boundaries of what is knowable. It pushes science forward, even if the path is uncertain. The pursuit of such questions, are we living in a black hole? What lies beyond the horizon of our reality, connects us to a long lineage of thinkers who dared to ask questions that seemed impossible. From the philosophers of ancient Greece to the quantum pioneers of the 20th century, humanity has always sought to understand the cosmos not just as it is, but as it might be. In contemplating the possibility that we exist inside a black hole, we continue that tradition, gazing upward at the stars, inward toward our own thoughts, and outward into the fabric of the universe, seeking meaning, structure, and truth. This framework also invites us to reevaluate our assumptions about beginnings and endings. Traditionally, a black hole is thought to be the end of a star's life cycle, a gravitational collapse that results in a singularity. The universe, on the other hand, is often conceived to have begun with the Big Bang, a sudden, singular origin event from which all matter, space, and time erupted. But if our universe is the interior of a black hole, then endings and beginnings might be two sides of the same coin. What appears to be an ending in one reality, the death of a massive star, could simultaneously be the birth of a new reality. This cyclical process collapses the notion of linear time and encourages a view of existence as recursive, iterative, and regenerative. Theoretical models of bouncing cosmologies further support this notion. In such models, the universe undergoes a series of contractions and expansions, with each cycle emerging from the remnants of the previous one. This aligns with ideas in loop quantum cosmology, where quantum gravitational effects prevent the formation of true singularities. Instead of infinite density, there is a bounce that creates the conditions for a new universe. If black holes operate on a similar principle, then the singularity inside may not be a point of no return but a quantum bridge, a passage from one cosmos to another. The Einstein-Rosen bridge, or wormhole, becomes a plausible mechanism for this transition, with the singularity acting as a kind of cosmic throat. Moreover, the very fabric of spacetime might be different inside a black hole. If we are inside one, the curvature of spacetime is not just an abstract property. It defines everything we know. Distance, mass, energy, and time itself may all be functions of that curvature. This leads us to the field of emergent gravity, which posits that gravity is not a fundamental force, but a byproduct of the statistical behavior of microscopic degrees of freedom. If this is true, then what we experience as gravitational attraction may be the large-scale effect of informational processes happening on the event horizon of the universe. This would be akin to the way pressure and temperature emerge from molecular motion. Under this lens, space itself could be an emergent phenomenon, a holographic projection from a deeper, more fundamental informational substrate. If the boundary of our universe encodes all the information within it, and if that boundary corresponds to a black hole's event horizon, then the entirety of our universe could be thought of as a 3D projection of 2D data. This profoundly alters how we think about reality. Physical laws, causality, and even consciousness may all be reflections of interactions occurring at the level of that encoded information. Such a perspective might also explain the uncanny mathematical harmony observed throughout the universe. The fine structure constant, the ratios of forces, the speed of light, and the laws of quantum mechanics all seem to fit together with inexplicable precision. In a black hole universe model, these values could be artifacts of the specific configuration of our parent black hole. Just as the temperature and pressure inside a container determine the behavior of a gas, the mass, spin, and charge of the black hole from which our universe emerged may determine the laws of physics we observe. This gives a context for fine-tuning that is neither random nor metaphysical. It is causal and emergent. This model also recontextualizes dark matter and dark energy. These mysterious components make up the vast majority of the universe, yet remain invisible and poorly understood. If our universe is the interior of a black hole, then dark matter and dark energy might be manifestations of its global geometry. Dark matter could correspond to the residual effects of mass distributions from the parent universe, or to gravitational influences from other universes embedded in the same higher-dimensional space. Dark energy, the force driving the acceleration of the universe's expansion, might be linked to the cosmological constant of the black hole's interior, or to the negative pressure generated by quantum fields that stabilize the geometry. Additionally, the acceleration of the universe's expansion might not be uniform or eternal. It could be influenced by the dynamics of the black hole in which we exist. If the parent black hole is absorbing new matter, rotating, or interacting with other cosmic structures, then those changes could ripple into our universe as shifts in energy, curvature, or entropy. This would make our universe far more dynamic and responsive than current models suggest. It implies that we are not isolated in a cosmic void, but intricately connected to a broader system of realities, each influencing the others through gravitational, informational, and quantum processes. The quantum nature of spacetime becomes central in this scenario. Quantum fluctuations, virtual particles, and entanglement may not be anomalies or footnotes in physics. They may be the foundation. If the universe is the interior of a quantum object like a black hole, then its most fundamental properties are likely to be quantum in nature. This lends credence to the idea of spacetime as a quantum foam, constantly fluctuating, probabilistic, and interconnected. The Planck scale becomes the fabric from which everything else is woven. Space and time are not the stage upon which reality plays out. They are participants in the play, actors with roles defined by the deeper script of quantum mechanics. This also transforms how we view consciousness. If everything in the universe is embedded within a black hole's interior geometry, then consciousness may not be an accidental byproduct of matter, but a feature of the universe's informational structure. Integrated information theory (IT) and other models suggest that consciousness arises from the complexity and integration of information. In a holographic, black hole-based universe, this information is fundamental. Consciousness may emerge not just in individual brains, but in the universe itself, as a distributed, emergent awareness arising from its own self-reflective structure. These ideas touch upon panpsychism, the view that consciousness is a fundamental feature of all reality, not just a late-stage evolutionary fluke. In a universe born within a black hole, where information, quantum entanglement, and geometry intertwine at the deepest levels, panpsychism becomes less mystical and more plausible. If information and its integration define experience, and if information is the most fundamental substance of the universe, then perhaps the cosmos itself experiences reality in some form. This again ties back to the holographic principle. If everything inside the universe is a projection of information encoded on its boundary, then perhaps minds, experiences, and even time itself are forms of data compression and pattern recognition. The flow of time may be a sequence of informational updates. Consciousness might be the engine that processes, observes, and integrates these updates, a cosmic witness embedded within the very structure of reality. At a metaphysical level, this model leads to a convergence between science and spirituality. Ancient traditions often speak of the universe as a great illusion or dream, unfolding from a singular source. The idea that we are living within a black hole, a self-contained, self-aware, mathematically exquisite structure, resonates with these teachings. The boundaries between observer and observed, self and other, time and eternity begin to blur. Science, long separated from mystical thought, begins to circle back toward the same insights from a different direction. This notion, that science and spirituality may not be as far apart as once believed, is an emergent theme in many cosmological inquiries, particularly those involving black holes and the nature of our universe. If we consider that we may be living within a black hole, and that such a structure is deeply intertwined with information, quantum mechanics, and emergent geometry, then it's only natural to contemplate the meaning of existence itself. The question, "Are we living in a black hole?" gradually morphs into a deeper question. What is reality, and why does it feel the way it does? In such a universe, the very experience of being human, of perceiving time, space, light, and emotion, is no longer merely biological or accidental. It becomes entangled with the shape and nature of space-time itself. Emotions may be neurochemical, yes, but the flow of those chemicals is ultimately guided by quantum fields within a universe that is itself a field, a dynamic, information-rich manifold perhaps wrapped within the event horizon of some higher-dimensional object. Our thoughts, therefore, do not just dance within our heads but may ripple across the curvature of a cosmic interior defined by the black hole's fundamental structure. The idea of time inside a black hole also deserves deeper contemplation. From the perspective of an external observer, time slows to a halt at the event horizon. But for someone inside, time continues to tick normally. This suggests that time may not be absolute but contextual, dependent on your location within a gravitational field. If we live within a black hole, then what we perceive as universal time may be entirely localized, an emergent dimension shaped by the geometry of the space we inhabit. This would make time a subjective phenomenon, differing not only from one galaxy to another but perhaps even from one region of space to another. This has radical implications for the concept of destiny and causality. In a universe born from a singular collapse, what would be the interior of a black hole? Every moment we experience could be the unfolding of a deterministic geometry. The past, present, and future may all be encoded into the topology of the space-time fabric, waiting to be experienced as the light cones of possibility collapse into specific sequences of events. This lends support to the block universe theory, where time is not a flowing river but a static landscape in which every moment exists eternally. We only move through it in our conscious perception. Furthermore, considering that our universe might be inside a rotating black hole, technically known as a Kerr black hole, opens up even more possibilities. Kerr black holes allow for ring singularities rather than point singularities and theoretically possess regions called ergospheres, where strange physical phenomena occur, such as the possibility of extracting energy from the black hole itself. Inside such a structure, the inner geometry becomes extremely complex, potentially allowing for closed time-like curves, paths through space-time that loop back on themselves, creating the possibility for time travel within the black hole's interior. Could the universe be structured in such a way? Might certain quantum behaviors, like retrocausality, where particles appear to affect past events, be shadows of this deeper structure? The quantum world often seems to defy classical notions of cause and effect, with entangled particles acting as though they share information instantaneously across vast distances. If all of space-time exists inside a black hole's interior, then perhaps these phenomena are not violations of causality, but expressions of a geometry where time and space are fundamentally linked in ways we do not yet understand. The vastness of this concept also invites us to consider the implications for multiverse theories. If each black hole potentially spawns a new universe, then the totality of reality may be an ever-branching tree of cosmoses, each governed by slightly different physical laws and constants. This may offer a solution to the anthropic principle, why the universe seems so fine-tuned for life. Out of countless black hole birth universes, we just happen to live in the one where the laws allow for consciousness to arise and wonder about its origin. This is not just a philosophical musing, it's a framework supported by increasingly sophisticated mathematics and simulations. Physicists such as Nikodem Poplawski have published peer-reviewed models proposing exactly this scenario, that the interior of a black hole could house a new universe, and that our own universe's Big Bang might in fact be a white hole, the time-reverse process of a black hole's collapse. In these models, the equations of general relativity can be extended through the singularity using certain torsion-based modifications, resulting in a bounce rather than an infinite collapse. It's possible that our universe, far from being a one-time fluke, is simply one node in a network of universes generated through gravitational processes in higher dimensions. In such a model, there may be black holes within our own universe that lead to new universes, and so on, an infinite cosmic fractal of birthing and dying realities. Each universe would carry the imprint of its parent, inheriting some aspects of its physical laws while mutating others through quantum fluctuations or boundary conditions. Reality becomes evolutionary in a deep, almost biological sense. This concept echoes theories in quantum cosmology where wave functions of the universe evolve according to their own rules. In these models, entire universes can be described by quantum states. Just as particles can exist in superposition, so too can universes, floating in a higher dimensional Hilbert space, collapsing into concrete realities only upon decoherence. If we are in a black hole, then perhaps the collapse of its wave function birthed our observable cosmos. It's even conceivable that our act of observation helps to crystallize this universe from among many probabilistic alternatives. From this vantage point, the question of free will becomes entangled with cosmology. Are we merely playing out a script written in the initial conditions of a black hole collapse? Or do our conscious choices influence the course of this emergent geometry? If consciousness is both a receiver and generator of information, then perhaps it plays a role in shaping the boundary conditions of the universe itself. Reality becomes a co-creation between mind and matter, observer and observed. This brings us full circle to one of the most profound implications of living in a black hole: the possibility that reality is fundamentally participatory. As physicist John Archibald Wheeler once proposed, the universe may not exist in a definite state until it is observed. In a holographic black hole model, this idea gains new depth. If all that we perceive is a projection from a boundary, and if our perceptions are themselves encoded on that boundary, then reality becomes a kind of infinite feedback loop, an echo chamber where experience and existence inform one another in an unending dialogue. This feedback loop might even serve as the mechanism of cosmic evolution. Universes that allow for conscious beings capable of reflecting upon their nature may be more likely to sustain complex structures and informational richness. In this way, black holes are not just endpoints. They are catalysts for creation, experimentation, and refinement. Each black hole becomes a crucible for a new universe, and each universe a potential home for life, consciousness, and eventually, understanding. If black holes are the wombs of new universes, then the cosmic cycle is not one of mere collapse and death but of rebirth and renewal. The entropy that builds in one universe might be the fertile soil from which another arises. And if that's the case, then our own universe, potentially nested inside a black hole, is not an isolated island but a continuation of a deeper, almost biological process of cosmogenesis. Imagine a cosmos where every black hole we observe is a seed, pregnant with the potential of a new universe. The gravitational collapse, far from being the end of information or structure, might be the start of a new set of initial conditions, encoded with the quantum properties of its parent universe but reshaped through the intense compression and transformation of a singularity, or a ring-like core and a Kerr geometry. In such a model, the arrow of time as we perceive it becomes a local phenomenon, specific to our particular pocket of reality, and the broader metacosmos may be timeless, filled with billions or even an infinite number of universes, each birthing and collapsing into one another like celestial lungs breathing existence. This view radically shifts how we understand evolution, not just biological, but physical and cosmic. Just as natural selection filters for traits that favor survival, perhaps there is a kind of selection among universes. Those that support complex structures like stars, galaxies, black holes, and ultimately, observers, may be more likely to spawn future universes. In this way, the universe may be tuning itself through a feedback process that is driven not just by physical law, but by informational resonance. The structure of one universe helps determine the structure of the next, possibly with incremental changes in fundamental constants, allowing for a form of cosmic heredity. This theory even has a name: cosmological natural selection, proposed by theoretical physicist Lee Smolin. In his hypothesis, universes that produce more black holes are more likely to reproduce, because each black hole potentially gives rise to a new universe. Over time, universes that are better at producing black holes become more common. Just like genes, laws of physics may be subject to a kind of Darwinian evolution. That would mean that we live in a universe optimized not for our existence per se, but for the formation of black holes. Our own emergence may be an unintended, but not insignificant, consequence of this optimization. Now consider what this means for our most pressing questions about reality. Why is the speed of light what it is? Why do electrons have their particular mass? Why does gravity behave according to an inverse square law? In a black hole origin universe, these questions might not have an ultimate metaphysical answer. They might simply reflect inherited parameters from a prior cosmic generation. In this view, constants are not constant across the multiverse. They are contingent, variable traits shaped by the birth conditions of the universe itself. Our universe, then, becomes a living fossil, a record of the conditions within the black hole that birthed it. The patterns we observe in the cosmic microwave background radiation, the distribution of galaxies, the behavior of dark energy, all of these may be subtle fingerprints left by that collapse. The Big Bang may not have been an absolute beginning, but a transitional state in an eternal cycle of cosmic gestation and reemergence. In other words, the singularity wasn't a point of infinite density, but a boundary between two phases of existence, one collapsing in, the other exploding out. Let's return to the concept of the event horizon. If our universe resides inside a black hole, then somewhere far beyond our observable limits, there may be an edge, a cosmological horizon that functions like the event horizon of a black hole. Just as light cannot escape a black hole's event horizon, information from beyond our universe's boundary cannot reach us. This boundary, from which space appears to expand, is not a wall but a limit, a surface that encodes the maximum amount of information our universe can hold. This limit might even be responsible for the accelerating expansion of the universe that we attribute to dark energy. In fact, some physicists argue that what we call dark energy might not be a force or substance at all. It might be a geometric effect caused by the horizon dynamics of our universe as a black hole interior. Just as a black hole's event horizon expands when matter falls into it, the cosmological horizon of our universe may expand as more spacetime is generated, leading to the accelerating expansion we observe. This would make dark energy not a mysterious force but a manifestation of the geometry and thermodynamics of spacetime. This model also provides a natural explanation for why the universe is so flat. In cosmology, flatness refers to the geometry of space being very close to Euclidean, with zero curvature. This requires extremely precise initial conditions in traditional Big Bang models, which seems improbable without fine-tuning. But if our universe is the interior of a black hole, then flatness is a natural consequence of the interior Schwarzschild or Kerr geometry. The horizon imposes geometric constraints that make the universe appear flat from the inside. But perhaps the most profound implication of this model is what it says about information. In a black hole, the surface area of the event horizon, not the volume, determines the maximum amount of information that can be stored within it. If our universe is the interior of such a structure, then everything we perceive, every galaxy, atom, and quantum field, might be encoded on a two-dimensional surface, projected inward like a hologram. Our reality, rich in three spatial dimensions and one of time, could be a high-fidelity illusion, a detailed manifestation of quantum information woven across a cosmic boundary. And yet, this illusion is not deception, it is emergence. Just as temperature emerges from the collective motion of particles, and just as a rainbow emerges from the interaction of light and water droplets, our universe may emerge from the entanglement patterns on a vast cosmic surface. We are not separate from the universe, we are it. We are not trapped inside a black hole, we are that black hole's dream of space, time, and self-awareness. As we stare deeper into space, we are not looking out, we are looking back, tracing the ripples of our cosmic birth, measuring the fingerprints left in light and gravity by the initial conditions of our own black hole origin. The further we look, the closer we come to understanding what we are. And as the instruments of science become ever more precise, and the models ever more complete, we inch closer to an answer that may be both scientifically rigorous and philosophically transformative. The notion that we live inside a black hole is not a fringe idea. It arises naturally when general relativity, quantum mechanics, information theory, and cosmology are brought together in harmony. It is a theory that honors complexity, welcomes paradox, and dares to ask, what if we are not just in the universe, but are the result of its deepest, most mysterious structures? What if our reality is not the end of a collapse, but the beginning of a new kind of being? The black hole becomes a symbol, not of destruction, but of creation, not of isolation, but of connection. Its event horizon becomes not a prison wall, but a screen upon which the film of our universe plays out in glorious, holographic detail. The singularity becomes a crucible of possibility, a point where space-time and logic itself dissolve, only to give rise to something radically new. And if we are that something, then we are not lost in the darkness, we are born from it. The blackness that shrouds a black hole, often thought of as a veil of destruction, may be something far more complex, a gestational boundary, a cocoon from which entire universes emerge. In this vision, our existence is not separate from the cosmic engine of transformation. We are embedded in its very fabric. And this brings us to a breathtaking possibility, one that intertwines physics with philosophy, astronomy with ontology. What if our lives, our consciousness, and even our thoughts are not accidental byproducts of a meaningless cosmos, but emergent expressions of an evolving multiversal intelligence? To understand this, we must expand the idea of a black hole far beyond its conventional image. Traditionally, black holes are described by three basic parameters: mass, charge, and angular momentum. This simplicity is known as the no-hair theorem. The idea that black holes, regardless of how they were formed, can be described by only these three features. Yet, recent research in quantum information theory challenges this notion. It suggests that black holes might encode far more information than previously thought. The quantum properties of the matter that collapses into a black hole could be imprinted subtly on the event horizon, preserved in quantum entanglement, and potentially retrievable through processes we are only beginning to understand. Stephen Hawking's famous information paradox questioned whether information that falls into a black hole is lost forever. If it is, this contradicts the fundamental tenet of quantum mechanics, that information is conserved. But if black holes preserve information on their surfaces, then perhaps the boundaries of our universe function in the same way. Every interaction, every quantum fluctuation, every moment of consciousness might be part of an intricate information network encoded at the edge of space-time. This brings us back to the holographic principle, which posits that the entire three-dimensional universe we perceive is actually a projection of two-dimensional data encoded on a boundary surface. If our universe is inside a black hole, then that surface is the black hole's event horizon, our cosmic boundary. This would mean everything we see, experience, and understand as real is a dynamic unfolding of quantum information encoded beyond our ability to observe it directly. This is not merely metaphor. It's a mathematical model supported by string theory and quantum gravity frameworks like the ADS/CFT correspondence, where a gravitational theory in a volume of space can be equivalent to a quantum field theory on the boundary of that space. The implications are staggering. Our universe could be a shadow of higher dimensional processes. The richness of our cosmos, the spiral arms of galaxies, the rhythm of orbital systems, the chemical choreography of life, may all be the emergent behavior of encoded boundary data. And this information might not be random. It might be organized, evolving, even selecting for patterns that increase complexity and structure. If so, then the emergence of conscious observers like us isn't an anomaly. It's part of a broader trend towards self-organizing systems that reflect, measure, and interact with the encoded information of the universe. In other words, the universe might be learning about itself through us. Our brains, composed of matter born in the hearts of stars, shaped by the laws of physics, and animated by biochemical currents, may be nature's way of interpreting its own code. We are the lens through which the cosmos sees itself. What if this isn't just a poetic idea but a physical reality? Consider pancomputationalism, the idea that the universe itself is a computational structure. Every particle interaction, every wave function collapse, every emergence of structure could be part of a vast computation. This doesn't mean the universe is a computer in the conventional sense, with wires and processors, but rather that it behaves according to logical rules that manipulate information. If our universe is inside a black hole, then its computational nature might be even more fundamental, driven by the transformations of information occurring at and within the event horizon. This also aligns with emerging concepts in loop quantum gravity and other theories of quantum spacetime. In such models, space and time themselves are quantized, built from discrete units that encode relationships and information. If we are within a black hole, these quantum grains of space could be the pixels of the holographic projection we call the universe. The seemingly continuous fabric of spacetime might be a smooth illusion created by the interactions of an unimaginably fine information network. Now consider time. In our everyday experience, time flows in one direction, from past to future. But within a black hole, time behaves strangely. In certain coordinate systems, what we call space and time exchange roles. This inversion means that falling into a black hole isn't just a journey through space, it's a transition in how reality is structured. Inside a black hole, the singularity isn't just somewhere you go, it's sometime you reach. If our universe exists in such an inverted domain, then the progression of time we experience might be a result of initial boundary conditions inherited from the black hole that birthed us. This leads us to wonder, is the arrow of time in our universe, this forward flow of entropy and causality, an emergent effect of boundary information? Is time a holographic illusion, a computational process encoded at the edge of our black hole universe? If so, then every moment of existence is a computational state transition in an evolving program written by the gravitational collapse of another cosmos. But what about the singularity, the central mystery of a black hole? In classical physics, a singularity is a point of infinite density and zero volume. But infinite values are signs that a theory has broken down, not that a physical object has reached some literal infinity. Quantum gravity is expected to resolve these singularities, replacing them with a more accurate description of extreme spacetime curvature. If our universe emerged from such a region, then its beginning might not be a true point, but a transitional zone where quantum spacetime fluctuated, merged, and recombined, giving birth to a smooth and expanding cosmos. In this model, the Big Bang was not a singularity, but a bounce, the outcome of a collapse that rebounded into expansion. The universe we see may be the aftermath of this rebound, shaped by the mass, spin, and information of the black hole that preceded it. This could even explain the uniformity of the cosmic microwave background radiation. The echoes of that rebound, filtered through the thermodynamics of horizon geometry, might imprint themselves uniformly across spacetime. And if that's the case, then every structure in the universe, galaxies, clusters, filaments, voids, is a blossoming of patterns seated in that rebirth. The complexity we observe is the unfolding of initial quantum symmetries broken during this transition. The matter and energy we measure, the laws we derive, the constants we use, all might be byproducts of a black hole's internal dynamics. We are riding the wave of a gravitational miracle, the space-time flower born from collapse. In this view, existence is not defined by stasis, but by process. Reality is not a fixed thing, but an unfolding. Black holes are not cosmic terminators, they are initiators, the gestational chambers of universes. The event horizon is not a wall, it's a membrane across which meaning transfers, encoded in quantum entanglement. The singularity is not an end, it's the seedbed of new dimensions. And so we circle back to our original question, are we living inside a black hole? We might be. The evidence is circumstantial but compelling, theoretical but rich with explanatory power. The mathematics suggests it, the thermodynamics supports it, the holographic principle reinforces it, and the behavior of space-time echoes it. We may be the children of collapse, the light born from darkness, the voice of a universe that was once only a whisper inside another. We are the memory of stars that never shone in our sky, encoded in the information flow of an event horizon we cannot see. To believe this is not to fall into fantasy. It is to stand on the shoulders of giants, Einstein, Hawking, Penrose, Smolin, and look beyond the veil of what is visible. It is to accept that the most profound truths may be those that hide not in the distance, but in the very nature of our perception. If we are inside a black hole, then reality is not smaller than we thought, it is infinitely grander. We are not trapped, we are entangled. We are not lost, we are connected. We are not alone, we are the voice of a cosmos that sings in gravitational harmony. The idea that we are living inside a black hole doesn't just challenge our understanding of space and time, it reshapes it entirely. In classical cosmology, the universe is vast and expanding, born from a singular explosion called the Big Bang, stretching out into what appears to be an infinite cosmos. But if our universe is the interior of a black hole formed in another parent universe, then this cosmic narrative is profoundly different. We are not expanding into an empty void. We are unfolding within a larger spacetime, possibly bounded by the event horizon of the black hole that birthed us. In this scenario, what we perceive as the limits of our observable universe are, in fact, the internal boundary of a vast gravitational enclosure. This idea also casts new light on the mystery of dark energy, the force that seems to be accelerating the expansion of the universe. Traditionally, dark energy is described as a cosmological constant, an intrinsic property of space itself. But if our universe resides inside a black hole, the perceived acceleration might be a geometric effect of residing in a curved, enclosed spacetime. The outward push we observe could be the effect of our universe expanding into a finite but curved region inside the parent black hole. The cosmological constant may not be a separate entity, but a natural consequence of this embedded geometry. This theory could help address the so-called cosmological constant problem, the discrepancy between the predicted and observed values of vacuum energy. If the vacuum energy we detect is influenced by the larger spacetime structure in which our universe is embedded, then our measurements might be incomplete, akin to observing water currents from inside a sealed aquarium. We only detect the local motion, not the larger forces acting on the entire system. And there's more. If black holes can birth universes, as some models suggest, then the laws of physics themselves might be subject to a kind of cosmic natural selection. This idea, proposed by physicist Lee Smolin in his hypothesis of cosmological natural selection, suggests that black holes are not endpoints, but reproductive events. Universes that are good at producing black holes become more likely to pass on their physical constants and structures. Over cosmic generations, universes with laws favoring black hole formation become more common. We, therefore, might be living in a universe finely tuned not because of an intelligent designer, but because of an evolutionary process at the multiversal scale. This would mean the values of the fundamental constants, like the strength of gravity, the masses of particles, and the cosmological constant, are not fixed by necessity or chance, but by a kind of survival of the fittest mechanism. Universes that evolve stable stars, which in turn collapse into black holes, are the ones that produce offspring. This evolutionary framework adds a profound layer of meaning to the cosmos. Our universe isn't just a random bubble. It might be a successful lineage in a long ancestral chain of universes. The mathematics supporting this scenario draws heavily on general relativity, quantum mechanics, and thermodynamics. In general relativity, the equations governing spacetime curvature admit solutions that resemble black holes with interiors that could, in principle, continue indefinitely. These solutions include metrics like the Schwarzschild interior and the Kerr solution for rotating black holes. In some extensions, these geometries lead not to singularities, but to bridges, connections to other regions of spacetime, or even new, causally disconnected universes. Quantum gravity attempts to resolve the singularity at the core of these models. In loop quantum gravity, for example, spacetime is quantized, and singularities are replaced by finite, but extreme, states where quantum effects dominate. This bounce model is consistent with a black hole turning into a white hole, an object that ejects matter and energy instead of capturing it. Our universe, then, could be the product of such a white hole, a birth of spacetime from the death of another. The implications stretch beyond cosmology into the heart of quantum theory. If the information that falls into a black hole is not lost but stored and transformed, then our universe could be a vast information processor, a quantum computer operating at cosmological scales. The fabric of spacetime, stitched together by entangled quantum states, may encode information with such efficiency that our entire observable cosmos is just a surface reflection of deeper informational processes occurring beyond our observational horizon. And what about consciousness in this framework? If the universe is fundamentally informational, then consciousness might be an emergent property of complex information systems. Our minds, products of brains composed of star-born matter, may not just be aware of the universe, they may be expressions of it. The observer, in quantum theory, plays a key role in collapsing probabilities into realities. Perhaps in a black hole universe, observers play an even deeper role, not just interpreting the code, but helping to shape it through their very act of observation. This takes us into the philosophical realm. What is reality if everything we experience is the internal projection of a boundary we cannot cross? Are we shadows on the wall, or are we the wall itself, experiencing its encoded information from within? The ancient allegory of Plato's cave seems eerily prescient. In the holographic universe, we are the shadows, but the shadows are real in their own domain, containing all the information of the objects casting them. The boundary is the source, and we are the manifestation. If we are living inside a black hole, then death and destruction are not the final truths we imagined. Creation springs from collapse, and the end of one universe may be the beginning of another. Black holes are not tombs, they are wombs. They do not signify the end of information, but the transformation of it. The universe may be an eternal cycle of birth, growth, collapse, and rebirth, each iteration governed by laws that evolve, adapt, and give rise to greater complexity. This paints a universe that is not static, not silent, but alive with process and change. A universe that learns, that experiments, that dreams in mathematical symmetries and awakens in the consciousness of its children. To live inside a black hole is not to be trapped, it is to be part of a cosmic narrative far grander than we ever imagined. And so, as we peer deeper into the nature of black holes, we are not looking at distant anomalies. We are looking at our origin story, written in the language of light and gravity. We are decoding our own birth, tracing the echoes of collapse that gave rise to stars, planets, and life. Every equation is a whisper from the beginning, every discovery a step toward understanding the infinite recursion of being. We are not apart from the universe, we are its echo, its code, its voice. And if that universe lies within a black hole, then we are not lost in darkness. We are the light that darkness gave birth to. If the notion that our universe lies within a black hole holds even a grain of truth, then the implications ripple outward into nearly every domain of physics, cosmology, and metaphysics. Let us now dive deeper, into the edge of known science and well beyond, where the structure of reality itself becomes the subject of inquiry. The boundary of a black hole, the event horizon, is not simply a region from which light cannot escape, it is a surface of information. This conclusion, popularized by physicist Jacob Bekenstein and later reinforced by Stephen Hawking, suggests that the entropy, or the information content, of a black hole is proportional to the area of its event horizon, not its volume. This principle became foundational in what we now call the holographic principle, the concept that all the information contained within a volume of space can be represented as encoded data on the surface that bounds it. When this idea is applied to the entire universe, the consequences are staggering. If our universe has a boundary, like that of a black hole, then everything we observe and experience may be a projection from this two-dimensional surface. This doesn't mean we are illusions, but rather that reality is encoded differently than we traditionally assume. In a way, we may be like characters in a cosmic simulation, not in the digital sense of a video game, but in the far deeper and more fundamental sense of information theory. This brings us to the ads/CFT correspondence, a discovery in string theory that suggests a precise relationship between a gravity-containing bulk space and a lower-dimensional boundary space without gravity. In this framework, a theory with gravity in a 5-dimensional anti-de Sitter space, ADS, is equivalent to a conformal field theory, CFT, on the 4-dimensional boundary of that space. This correspondence hints that the laws of gravity, and by extension, spacetime, might emerge from lower-dimensional, non-gravitational physics. While our universe does not appear to be an ADS space, we see evidence of a positive cosmological constant, indicating de Sitter geometry. The correspondence opens the door to a radical idea. Spacetime might be emergent, not fundamental. Just as temperature and pressure are emergent properties of the statistical behavior of molecules, space and time could be the large-scale behavior of more primitive entities, perhaps entangled quantum bits on a horizon surface. And this ties back into the black hole universe hypothesis. If the surface of the black hole that birthed us encodes all the information about our universe, then we might truly be a projection, a realization of information stored at the boundary. Every galaxy, every particle, every atom in your body, encoded on a cosmic sphere, possibly as small as a few dozen kilometers in radius from the outside perspective, yet experienced by us as billions of light years wide. Now, consider how such a universe might come into being. When a massive star collapses, it forms a singularity, at least according to classical general relativity. But quantum effects, especially those predicted by loop quantum gravity and string theory, may prevent an actual singularity from forming. Instead, as the collapse continues, spacetime may reach a critical point where quantum gravity bounces the collapsing mass into a new expansion phase. From the perspective of the parent universe, this is hidden behind the event horizon, but within the black hole, a new expanding region of spacetime, what we call a universe, is born. And within that bounce, the conditions of the new universe, its physical constants, its symmetry groups, its vacuum state, might differ from those of the parent universe. This randomness could explain the fine-tuning of our own universe. We observe just one outcome out of a vast landscape of possibilities. Most black holes may not create universes with stable matter or long-lived stars. But ours did. And that makes all the difference. Within our universe, we see the imprint of this origin in the cosmic microwave background, in the accelerating expansion, and in the laws of physics that seem finely tuned for complexity. Could it be that these fingerprints are not just accidents, but ancestral features, traits passed down from a lineage of universes that have evolved through black holes? This model even offers a potential explanation for the arrow of time. In most physical laws, time is symmetric. The equations work the same whether time moves forward or backward. But our experience, and the second law of thermodynamics, shows a clear forward direction, from order to disorder, from low entropy to high. If our universe began in the high curvature, low entropy state of a black hole interior, then the emergence of time itself might be a consequence of that initial asymmetry. As the universe expands and cools, entropy increases, giving rise to the temporal flow we experience. Moreover, this framework reshapes how we might view other black holes. If our universe is a black hole, then perhaps other black holes in our universe are themselves the seeds of new universes. Each black hole could contain a budding cosmos with its own time, space, matter, and laws. From our perspective, those interiors are forever hidden behind event horizons. But from within, they might be vast, complex, and teeming with life. This leads to a picture of a multiverse, not of isolated bubble universes floating in some higher dimensional space, but of nested spacetimes, each born from the collapse of a star or a galactic core in its parent universe. And this nesting could go on indefinitely. Our universe could be several generations deep in a cosmic family tree of black holes birthing universes. Each generation contains the seeds of the next, like a fractal growing new branches forever. The ultimate structure of reality, then, is recursive, layered, and endlessly generative. It also changes how we think about destiny. If the universe is a black hole, then it has an outer boundary we will never reach, a horizon beyond which lies the parent universe. But just as we were born from collapse, we may give rise to our own children. As stars in our universe die and form black holes, they may birth entirely new realms of existence. We are not only products of the cosmos, we are its reproductive organs, its agents of continuity, its bridges to the future. Our actions, our science, our curiosity, our explorations, are not meaningless in the face of cosmic immensity. They are echoes of the universe understanding itself, learning from itself, and possibly shaping the futures of the children universes that may arise from us. This is not science fiction. These are real hypotheses grounded in the frontier of theoretical physics. They may not yet be testable in the traditional sense, but they offer explanations for phenomena we observe and guide us toward new questions. They suggest that black holes are not the end, but the beginning of something astonishing. They whisper that space, time, and reality are far stranger and more beautiful than we ever imagined. Perhaps one day, our descendants will learn to peer beyond the event horizon. Perhaps they will send signals to the boundaries of our black hole to understand what lies beyond. Or perhaps they will create black holes of their own, initiating new universes, passing on the spark of curiosity to whatever forms of consciousness arise there. If we are living inside a black hole, then we are part of an unbroken lineage of cosmic creation. We are not prisoners of gravity, we are its children, born in fire and folded space, destined not just to observe the universe, but to extend its legacy. And in the quiet of the night, when we look up at the stars and wonder why we are here, the answer may be this: we are here because a star died. And in that death, it gave birth to everything. It is not merely poetic to imagine that a dying star's collapse gave rise to our universe. It might be the literal truth. What begins as a star exceeding a critical mass threshold ends not in oblivion, but in transformation. As its course succumbs to its own gravity, a black hole forms, and beyond the veil of its event horizon, a singularity is said to arise. But this singularity, often thought of as a point of infinite density, is likely a placeholder for unknown physics, a signal that our current theories break down at such extremes. What if instead of a singularity, there is a bounce? A reversal? A cosmic rebirth? Loop quantum gravity, an approach to unifying general relativity with quantum mechanics, proposes that space itself is quantized, made up of discrete units, or quanta, of spacetime. Within this framework, gravity becomes repulsive at very small scales, possibly preventing the formation of true singularities. Instead, a black hole's collapse could reach a point of maximal density, and then rebound, creating a new inflating region of spacetime, a new universe. From the outside, this is just a black hole. From the inside, it's the Big Bang. This kind of bounce cosmology offers a fascinating way around the classic singularity problem. It also provides a mechanism for creating universes that inherit some properties from their predecessors. In this sense, natural selection could apply on a cosmic scale, universes that are better at creating black holes, by virtue of their physical laws and constants, give rise to more offspring. Over many generations, universes evolve to become black hole factories. Our universe, with its numerous massive stars and supermassive black holes at galactic centers, fits this profile remarkably well. In fact, this idea is part of what's known as cosmological natural selection, proposed by physicist Lee Smolin. Just as biological evolution favors traits that increase reproductive success, cosmic evolution might favor laws of physics that increase black hole production. This startling idea could even offer a non-anthropic explanation for the fine-tuning of physical constants. We live in a universe that permits life not because we are lucky, but because the same properties that allow complex chemistry also enable black hole formation. Life is not the goal, but a byproduct of cosmic reproduction. If the black hole universe hypothesis is true, then black holes are more than celestial trash compactors. They are the wombs of creation, gateways to realms we can scarcely imagine. And this brings us to an even more radical implication: the nature of causality itself. Traditional physics follows a linear chain of cause and effect bound by time. But in a multiverse shaped by black holes birthing universes, causality may become cyclical, fractal, or branching. Universes give rise to other universes, which in turn may evolve to create more black holes and more universes. This cascade of causation blurs the lines between parent and child, between origin and destiny. Moreover, time inside a black hole behaves very differently from time outside. As one approaches the event horizon from the outside, time appears to slow to a standstill. Yet for an observer falling into the black hole, time proceeds normally. This paradoxical behavior challenges our intuitive understanding of temporal flow. If we are inside a black hole, then our experience of time may be drastically different from that of the external universe that gave rise to us. We might exist in a nested temporal frame, our clocks ticking forward while the outer universe watches our entire history unfold in slow motion, or even as a frozen snapshot. Now consider the geometry of space-time. Inside a black hole, according to classical general relativity, the roles of space and time can swap. The radial coordinate, which measures distance from the center, becomes time-like, and time becomes space-like. This reversal suggests that falling into a black hole is not a journey to a place, but a journey to a moment, a future moment from which no return is possible. But if the black hole contains a new universe, then this singular moment may stretch out into an entire cosmic timeline. What was once the end becomes a beginning. This idea reshapes our notion of the Big Bang. In standard cosmology, the Big Bang is a singular origin, a point of infinite density and zero volume from which space, time, and matter emerged. But if the Big Bang is the interior of a black hole, then it is not a point, but a passage. The singularity becomes a bridge, a link between one universe's end and another's beginning. In some speculative theories, such bridges are called Einstein-Rosen bridges, or wormholes. While traversable wormholes remain purely theoretical, the idea that black holes might connect universes is gaining traction in theoretical physics. Let us now reflect on the philosophical implications. If we are inside a black hole, then our entire universe is causally disconnected from the one that birthed us. We cannot send signals back, nor receive any. We are sealed in a cosmic cocoon, an embryonic reality gestating in the dark. Yet we are not alone. Every black hole in our universe could be another such cocoon. The cosmos may be teeming with nascent realities, each one a pocket universe with its own destiny. This framework forces us to reconsider the role of consciousness and intelligence. In the grand scheme of cosmic evolution, consciousness might not just be an accident, it could be a mechanism. Intelligent beings like us may eventually manipulate black holes, shape space-time, and perhaps seed new universes deliberately. In doing so, we would take part in the creative process of the cosmos, becoming midwives of existence. Such speculations border on metaphysics, yet they are grounded in serious physics. The boundaries between science and philosophy blur at these scales. To think of the universe as alive, as reproducing, as evolving, this is not mysticism, but a legitimate line of inquiry in theoretical cosmology. What about observable evidence? Can we ever test the hypothesis that we live in a black hole? This is challenging, but not impossible. Certain signatures in the cosmic microwave background might hint at a boundary or topology inconsistent with infinite flat space. Quantum gravity may reveal limits to the amount of information in the universe, consistent with a holographic surface. And future generations of telescopes and experiments may detect subtle features that suggest our universe has an edge, not a spatial edge, but an informational one. Another line of evidence might come from understanding black hole interiors. If we can develop a theory of quantum gravity that accurately describes what happens beyond the event horizon, we may find that the conditions there mirror those of our early universe. This would lend credence to the idea that universes form inside black holes. But such a discovery would require a leap in theoretical and computational physics, one we may yet achieve. One tantalizing possibility is that the entanglement structure of quantum fields across the horizon encodes the geometry of spacetime itself. This is the essence of the ER equals EPR conjecture proposed by physicists Juan Meldacena and Leonard Susskind. It posits that Einstein-Rosen bridges, wormholes, and quantum entanglement, Einstein-Podolsky-Rosen pairs, are two sides of the same coin. If true, then the fabric of the universe is woven from entanglement. Black holes are not isolated anomalies, but hubs in a vast entangled network. If our universe is such a hub, then perhaps all of space-time is a manifestation of quantum information. Our universe is not, inside, a black hole in the traditional sense, but rather is the internal realization of a boundary condition, an emergent domain arising from information constraints on a horizon surface. As we stretch our imagination to grasp this possibility, we must also confront its limits. Our tools are mathematical, our observations bounded, and our minds shaped by evolutionary pressures to understand the immediate world, not the infinite. And yet we try. We ask questions that reach beyond survival, beyond comfort, beyond reason. We ask because we are conscious, and consciousness demands context. It demands origin. It demands purpose. Perhaps the most important takeaway from this exploration is not whether the black hole universe hypothesis is literally true, but what it represents, a deepening of our quest to understand existence. It challenges us to think beyond what is observable, to entertain ideas that reshape our mental universe. And maybe, just maybe, it will lead us to a new revolution in physics, one that unites the quantum and the cosmic, the inner and the outer, the observer and the observed. At the deepest level of inquiry, we find ourselves drawn not only to the architecture of space and time, but to the implications of that architecture on our place in the cosmos. If our universe is the interior of a black hole, then we are inhabitants of a reality born from the collapse of a previous cosmos, nested, recursive, self-sustaining. But beyond the poetry of such a thought lies rigorous scientific speculation, which demands that we ask, how would such a universe behave? Could the physics of a black hole explain the behavior of our universe? Could it account for the expansion, the entropy, the very conditions that allow for life? One of the foundational ideas that supports the black hole universe hypothesis is the similarity between the mathematical structures of black hole thermodynamics and cosmology. Stephen Hawking and Jacob Bekenstein first uncovered that black holes are not entirely black. They radiate energy due to quantum effects at their horizons, a phenomenon now known as Hawking radiation. This radiation implies that black holes possess a temperature and entropy. Remarkably, the entropy of a black hole is proportional not to its volume, but to the area of its event horizon, suggesting a profound connection between information and surface geometry. This revelation gave birth to the holographic principle. The holographic principle, proposed by Gerard T. Hooft and further developed by Leonard Susskind, posits that all the information contained within a volume of space can be described by data encoded on the boundary of that space, much like a hologram. This principle is most rigorously explored in the anti-de Sitter/conformal field theory, ADS/CFT, correspondence, discovered by Juan Meldacena. In this duality, a theory of gravity in a bulk spacetime is equivalent to a quantum field theory on its boundary. While our universe is not ADS, the correspondence has inspired the idea that our universe might be a holographic projection from a higher dimensional boundary. If we live inside a black hole, the boundary of that black hole, its event horizon, could serve as the holographic screen from which our universe is projected. The idea is radical but coherent. The entropy of the observable universe is immense but finite, and it aligns well with the notion that there is a limit to how much information can be stored in any region of space. This is consistent with the entropy of a black hole of equivalent size. In other words, our universe's information budget may match that of a black hole with the same radius. This line of reasoning supports the idea that the universe's structure is determined by constraints imposed at a horizon. If we model the universe as a three-dimensional surface inside a four-dimensional black hole, we can begin to describe spacetime as an emergent phenomenon. Gravity, in this view, is not a fundamental force but an emergent one, arising from changes in the entanglement of quantum fields across the horizon. This concept, developed in part by physicist Eric Verland, reframes gravity as a thermodynamic effect rather than a fundamental interaction. What does this mean for cosmology? If our universe's expansion is driven by entropy maximization, by the statistical tendency of systems to evolve towards states of higher disorder, then cosmic inflation, dark energy, and even the arrow of time may be explained not by separate mechanisms, but as natural consequences of entropic processes occurring within a bounded black hole-like structure. In this picture, the bang of the Big Bang is not a unique singularity, but a common feature of every universe formed within a black hole. Each black hole in a parent universe may spawn a daughter universe with its own laws and constants, each obeying the principles of holography and thermodynamic equilibrium. From here, we must consider how such a system could account for the specific characteristics of our own universe. Why do we observe the cosmological constant to be so small but non-zero? Why does the universe appear flat, homogeneous, and isotropic at large scales? And why do physical laws seem fine-tuned for the emergence of complexity? These are long-standing problems in physics, often addressed via the anthropic principle. We observe this universe because it permits observers like us. But if we adopt the black hole universe hypothesis, a new answer emerges. Perhaps these characteristics are not arbitrary, but inherited, passed down from a parent universe that itself was conducive to black hole formation. Universes that expand too quickly or too slowly, that lack stable particles, or that fail to form stars, may not produce many black holes. Thus, they leave behind few or no offspring. Over cosmic timescales, the multiverse becomes populated with lineages of universes that naturally evolve toward configurations that favor black hole production, and by extension, complex structures like stars, planets, and life. This evolutionary process is blind, indifferent, but not random. It is shaped by selection pressures, not for life per se, but for black holes. And since the conditions favorable for black holes overlap with those favorable for life, we find ourselves in a universe not by chance, but by necessity. In this way, the black hole universe hypothesis provides a teleological framework for cosmology without invoking design. We must now explore another critical aspect of this hypothesis, the causal structure of spacetime. Black holes exhibit a one-way causal boundary at the event horizon. Nothing that crosses it can return. If we live inside such a structure, then the initial conditions of our universe were set by processes we cannot observe directly. This causal disconnection presents both a challenge and an opportunity. It challenges us because we cannot empirically access the parent universe. But it also offers a solution to certain paradoxes. Consider the black hole information paradox. According to classical general relativity, information that falls into a black hole is lost forever. But quantum mechanics forbids the loss of information. Hawking's discovery of black hole radiation appeared to violate this principle, creating a major inconsistency. If the information is not lost, where does it go? In the context of the black hole universe hypothesis, the information may not be lost but transferred, re-expressed as the configuration of the new universe inside the black hole. This would preserve unitarity, the foundational principle that information is conserved in quantum mechanics. The process of universe creation becomes not a loss of information, but its transformation, an encoding from one reality to another. In this way, the child universe becomes the information carrier of the parent's collapse. The laws, constants, and initial conditions of the new universe become a message from the old, albeit one we cannot decrypt without understanding the full language of quantum gravity. Let us now expand our scope. If our universe is a black hole, then time as we experience it may not be universal. Time within a black hole flows differently than outside. An external observer sees time slow to a halt at the event horizon. From their perspective, infalling matter appears frozen. But to the infalling observer, time proceeds normally. If this analogy holds, then perhaps what we call cosmic time is a localized phenomenon, unfolding within a greater timeless background. Perhaps the birth, life, and death of our universe is a single moment on a higher dimensional canvas. In this view, the arrow of time is not a feature of the universe as a whole, but of the particular path we follow through spacetime. Entropy increases not because time moves forward, but because our path takes us through regions of greater complexity. If time is emergent, as many physicists now believe, then so too is causality. The past and future are not fixed absolutes, but contextual relationships among events. This radical view is supported by developments in quantum foundations. Experiments in quantum entanglement, delayed choice, and quantum teleportation suggest that information is not bound by classical constraints. In some interpretations, like the block universe, or eternalism, all events, past, present, and future, exist simultaneously. Our experience of temporal flow is an emergent illusion, born of consciousness navigating a static landscape. If so, then the creation of a universe inside a black hole is not a sequence of events but a structure in space-time. The parent universe collapses, a black hole forms, and a new universe blooms within. To us, this is a history. But in a block universe, it is a geometry, a connected pattern, fixed and timeless. As we contemplate this, we must also consider the ultimate fate of our universe. If it is a black hole, will it eventually evaporate? Will it emit Hawking radiation and shrink to nothingness? If so, what happens to the universe inside? Does it too evaporate, or is it insulated from its parent's demise? The answer depends on the details of quantum gravity. Some theories suggest that Hawking radiation does not destroy the information within, but returns it to the parent universe in a scrambled form. Others suggest that the internal universe continues unaffected, forever isolated. If so, then the death of the parent black hole marks only a transition, a shedding of the cocoon that once enclosed the growing cosmos. Ultimately, the black hole universe hypothesis challenges us to rethink everything. Not just space and time, but cause and effect, beginning and end, self and other. It invites us to view the cosmos not as a singular object, but as a process, a dance of creation and collapse, of birth within death, of endless recursion. And in that infinite regression, we may find both humility and wonder. Humility, because we are tiny participants in a vast and possibly eternal cycle. Wonder, because we can perceive it, ponder it, and even strive to understand it. The story does not end here. What if the very nature of existence is recursive, not just in the structure of universes within black holes, but in the mathematical fabric underlying all reality? Recursion appears across natural systems, from the self-similar branches of a fern to the nested structure of galaxies. If this pattern holds at the cosmic scale, then perhaps the universe is not only within a black hole, but the laws that govern it are echoes of higher-level rules that themselves emerge from deeper, even more abstract levels of reality. This concept touches the core of what physicists call emergentism, the idea that complexity and structure arise from simpler, often unrelated elements. Gravity, for example, might emerge from quantum entanglement. Space might emerge from networks of information. Time might emerge from causal relationships. The universe, in this view, is not a static arena but a computation, a constantly updating state machine where patterns at one scale give rise to entirely new phenomena at another. One striking model along these lines is loop quantum gravity, which proposes that space itself is quantized, that there is a smallest possible unit of space, a quantum of volume, just as there is a smallest unit of light, the photon. According to this theory, space-time is woven from tiny loops of quantum threads. These loops do not exist within space, they are space. When billions of them interact, they form the geometry we experience. If loop quantum gravity is correct, then black holes, and by extension, universes that might exist within them, are not singularities, but bounces. The collapse of a massive star into a black hole does not end in a point of infinite density, but instead reaches a smallest size and then re-expands, forming a new region of spacetime, a new universe. This is called a quantum bounce, and it suggests that the Big Bang itself was not the beginning, but a transition, just one in a possibly infinite sequence of contractions and expansions. This idea is mathematically supported in loop quantum cosmology, a specialized field that applies the principles of loop quantum gravity to the entire universe. Instead of starting with an initial singularity, the universe undergoes a bounce from a prior contracting phase. If true, then our current expansion phase is just a chapter in an eternal cosmological cycle, where universes give birth to other universes through black hole formation. And if such a cycle exists, the information from one universe could be subtly encoded into the next, not through direct inheritance, but through probabilistic imprinting. Constants such as the speed of light, gravitational strength, and even the mass of the electron might be selected over cosmic generations in a kind of cosmological Darwinism. those parameter sets that favor complexity and black hole formation, are naturally selected. Over eons, this would shape a multiverse not randomly, but toward increasing sophistication. If this all sounds philosophical, it's because we are approaching the frontier where science meets metaphysics. We can no longer rely solely on testable predictions. Instead, we must look for coherence, elegance, explanatory power. The black hole universe hypothesis does not yet yield testable predictions in the traditional sense. But it offers a framework that explains why our universe appears the way it does, flat, expanding, governed by fine-tuned constants, and filled with black holes. This framework also has implications for the arrow of time. Traditionally, time flows in one direction because entropy increases. But what determines the initial low-entropy state of the universe? If our universe emerged from a black hole, then the apparent, low-entropy, beginning might be a projection of a highly complex structure compressed through a bounce. The information of the parent universe could be folded into the initial conditions of the child universe, not in an ordered way, but in a way that allows complexity to arise again. In this light, the second law of thermodynamics is not merely a statistical law of disorder, but a signature of a deeper process, the unfolding of inherited structure. Our universe might not be random, but purposeful, not by design, but by the logic of cosmic iteration. Even quantum mechanics, with its probabilistic nature and wave function collapses, might make more sense in this context. The indeterminacy of quantum events could reflect the interface between the emergent reality of our universe and the deeper layers of recursion beneath it. Just as a computer program produces outputs based on invisible instructions, the quantum world might be that output of a deeper informational substrate we do not yet perceive. And what of consciousness? If the universe is recursive, emergent, and informational, then perhaps consciousness, too, is not a fluke but a structural inevitability. Complex, self-referential systems like brains arise not randomly, but because they are favored by the same evolutionary forces that shape universes. Just as black holes give birth to universes, perhaps conscious observers give birth to meaning. In this sense, consciousness and cosmos are linked, not causally, but reciprocally. One interprets the other. One enables the other to be known. As this hypothesis matures, it will require new mathematics, new tools, new philosophies. We may need to unify general relativity, quantum mechanics, thermodynamics, and information theory into a single, coherent framework. This is the dream of a theory of everything, not merely a unification of forces, but a unification of principles, emergence, recursion, and the holographic encoding of reality. The black hole universe theory is not just a hypothesis about where we live. It's a proposal for what existence itself means. We are not drifting in a void, alone in a singular event. We are part of a lineage, descendants of universes, ancestors of others, interconnected through horizons we cannot yet cross. And if that's true, then every black hole in our universe is not a dead end but a seed. Each one might be blooming, slowly, invisibly, into a cosmos of its own, with galaxies, stars, life, and questions of its own. If each black hole potentially gives rise to a new universe, then the total number of universes could be unimaginably vast. Some might be barren voids of unstable particles and warped geometries. Others might teem with complex structures, stars, and perhaps even life. Each would inherit subtle properties from the conditions of its parent universe's black hole, the mass, spin, charge, and quantum information compressed at the moment of collapse. And yet, despite this inheritance, no two universes would be exactly the same. Variations would emerge, some slight, others profound. In this sense, every black hole becomes a kind of experiment, nature's way of exploring the full spectrum of possibility in the cosmic landscape. This leads us to the staggering possibility that our universe may not be typical, it may be exceptional. Not in the sense of being uniquely important, but in the sense of being particularly well-suited to the development of complexity and consciousness. If most universes are short-lived or unstable, those that can sustain complexity for billions of years, like ours, may be extremely rare. But rarity does not mean uniqueness. In an infinite multiverse birthed by countless black holes, even the rarest types of universes will exist in abundance. And this raises the question, why do we find ourselves in such a universe? This is where the anthropic principle comes into play. According to the weak anthropic principle, we can only observe a universe compatible with our existence. In other words, we shouldn't be surprised to find ourselves in a universe that supports life, because we wouldn't be here to ask the question otherwise. However, the black hole cosmology hypothesis provides a more profound framework for this principle. If universes that create black holes give rise to more universes, and black holes are more likely to form in universes with stable matter and complex physics, then there's a kind of natural selection occurring. Universes like ours, capable of producing black holes, become more common over time. And the same conditions that favor black holes, stable stars, long-lived structures, rich chemistry, also favor the emergence of life. In this view, the anthropic principle is not just a tautology, but an explanatory feature of cosmic evolution. It tells us why the universe is the way it is, not by invoking design, but by recognizing the feedback loops that reward structure, complexity, and recursion. It is a theory of cosmic evolution that parallels biological evolution, not in the mechanisms, but in the logic. Now let's explore a deeper layer of this hypothesis. What happens to information that falls into a black hole? This has been one of the most vexing puzzles in modern physics, the so-called black hole information paradox. According to classical general relativity, anything that falls into a black hole is lost forever, crushed into a singularity. But quantum mechanics insists that information can never be destroyed. The tension between these two principles has driven decades of debate. Stephen Hawking famously proposed that black holes slowly evaporate through a process called Hawking radiation, emitting particles over time until they vanish. But if a black hole evaporates completely, what happens to the information it swallowed? Is it erased? Or somehow encoded in the outgoing radiation? Resolving this paradox is essential, not just for black hole physics, but for the very foundations of reality. One promising answer comes from the holographic principle, a concept developed by Gerard T. Hooft and Leonard Susskind. It suggests that all the information contained within a volume of space can be described by data encoded on its boundary. In the case of a black hole, the three-dimensional information about everything that fell in might be encoded on the two-dimensional surface of its event horizon. In this sense, the black hole is a hologram. Its surface contains all the data needed to reconstruct its interior. If we extend this idea to the universe itself, we arrive at a breathtaking possibility. The entire cosmos may be a holographic projection. What we perceive as three-dimensional reality may emerge from information encoded on a distant, lower-dimensional boundary. In this model, space and time are not fundamental. They emerge from the entanglement and structure of underlying information. This holographic view aligns beautifully with the black hole universe hypothesis. If our universe is the interior of a black hole in a higher dimensional space, then its boundary, the event horizon, might hold the key to understanding everything within it. Perhaps we are living inside a cosmic hologram, a projection cast by the surface of a collapsed star in some parent universe. This brings us full circle to the nature of observation and consciousness. If reality is fundamentally informational, then conscious observers, who process and interpret information, are not anomalies but essential participants. The act of observation may not merely reveal reality but help generate it. This is one interpretation of quantum mechanics, that observation collapses the wave function and brings specific outcomes into being. In a holographic, black hole-born universe, observers might play a more central role than ever imagined, not as creators of the universe, but as co-participants in its unfolding. So where does this leave us? Are we living inside a black hole? Perhaps not definitively, not yet. But the evidence mounts, the models grow stronger, and the implications grow deeper. We find ourselves at the edge of knowledge, staring across the event horizon of understanding, peering into a mystery that may never fully yield its secrets. And yet, in striving to comprehend it, we become something greater. Not because we solve the mystery, but because the mystery transforms us. If our universe is the interior of a black hole, the implications for the origin of time itself are staggering. Inside a black hole, the fabric of spacetime is warped so drastically that the radial coordinate, which is usually considered space, effectively becomes time-like. This inversion means that once something crosses the event horizon, moving inward toward the singularity is not a choice but a necessity. It's as inevitable as moving forward in time. Applying this logic to our own universe, if we are indeed inside a black hole, then the direction we perceive as forward through time could be, from an external perspective, a spatial movement toward a central singularity of our own universe. But what would that singularity be? In standard cosmology, the beginning of time, the Big Bang, represents a singularity. Not a point in space, but a boundary in time, the moment when all known laws of physics break down. If our universe is the interior of a black hole, then our Big Bang could correspond to the moment of collapse of a massive star in a higher dimensional parent universe. The singularity at the core of the black hole in that parent universe would map onto our own Big Bang. This raises the idea that the arrow of time we experience is actually the path inward toward that singularity, though in our perspective, it looks like an expanding universe moving forward in time. What makes this theory even more compelling is that it solves one of the deepest problems in cosmology, the question of what came before the Big Bang. In standard models, the singularity is a point where the theory breaks down, and before becomes meaningless. But in black hole cosmology, before, the Big Bang is simply the external region of a collapsing star in another universe. Our universe's birth is no longer an uncaused event, it is the natural consequence of a physical process that took place in a higher dimensional space. Another layer to this is the role of entropy. In our universe, the second law of thermodynamics governs that entropy, or disorder, must always increase. The early universe was in a state of incredibly low entropy, and the mystery of how such an improbable state came to be has puzzled scientists for decades. But if our universe formed from the collapse of a highly ordered star, this might explain the initial low entropy. It was inherited from the parent universe's conditions. As time progresses, or as we move inward in the black hole analogy, entropy increases, just as it does in any closed system. This aligns our cosmological arrow of time with the thermodynamic arrow, and the psychological arrow, the direction we experience as the passage of time. Now imagine how this structure scales. If every black hole gives rise to a universe, and every universe contains stars that become black holes, the entire multiverse becomes a self-replicating fractal, a cosmic tree of branching realities. Each node is a universe born inside the black hole of its parent, and each branch gives rise to further offspring. This creates a natural evolutionary process, where universes that are better at forming black holes are more likely to proliferate. Over countless generations, the physical laws that promote the creation of black holes, and by extension, long-lived stars, complex chemistry, and potentially life, become more and more common. This idea is known as cosmological natural selection, first proposed by physicist Lee Smolin. According to this theory, the universe is not just a static container of matter and energy, but an evolving system with its own form of heredity and variation. Universes reproduce through black holes, and the parameters of each universe, like the strength of gravity, the mass of particles, or the number of dimensions, are slightly altered in each offspring. In this view, our universe is not random. It is finely tuned for the emergence of black holes, and as a side effect, it is also finely tuned for the emergence of life. It requires only the power of selection, the same principle that guided the evolution of life on Earth. Over billions of cosmic generations, universes that can give rise to complexity will inevitably become more common. But how could we ever test such a theory? The answer lies in the search for signatures. If black hole cosmology is correct, we might expect to find subtle clues in the structure of our universe. For instance, the geometry of space-time could bear imprints of higher dimensional physics. The values of fundamental constants might show patterns that suggest they were selected for optimal black hole production. Even the cosmic microwave background, the radiation left over from the Big Bang, might carry evidence of its unusual origin. Furthermore, The information paradox mentioned earlier could hold the key to understanding the boundary between our universe and the parent universe. If the information that falls into a black hole is not lost but encoded on its surface, then perhaps everything that happens in our universe is likewise encoded on a boundary we cannot yet perceive. This would mean that everything we know, all galaxies, stars, planets, and people, are manifestations of a deeper informational structure inscribed on a distant, invisible horizon. This is not just abstract speculation. Experiments at the cutting edge of physics, such as those conducted at CERN's Large Hadron Collider, are probing the fabric of spacetime for hints of extra dimensions, microscopic black holes, and deviations from standard quantum mechanics. Astrophysical observations are testing the limits of general relativity in extreme environments, such as neutron stars and supermassive black holes. Theoretical breakthroughs, like those in string theory and loop quantum gravity, are exploring the deep connections between geometry, entropy, and information. And yet, the most profound implications of living inside a black hole may not be physical, but philosophical. If our universe is the interior of a black hole, then the very concepts of inside and outside become blurred. We are no longer isolated beings in a vast, indifferent cosmos. We are the interior process of a cosmic event. Our existence is not an accident, but a transformation, an unfolding of structure, meaning, and awareness from the collapse of something older, something beyond. This raises deep questions about the nature of identity and scale. If we are inside a black hole, what is our relationship to the parent universe? Are we separate or connected? Is there a form of communication possible between the inside and the outside? Could the birth of our universe have created observable effects in the parent universe, gravitational waves, bursts of energy, or even alterations in its own cosmic structure? And could the collapse of black holes in our universe one day give rise to entirely new universes, populated by beings pondering the same questions? In a sense, the black hole model collapses the boundaries between physics and metaphysics, between science and existential inquiry. It invites us to consider not just where we are in space, but where we are in reality. If every black hole is a portal to a new cosmos, then reality is not a fixed landscape. It is an ongoing genesis, a continuous flowering of possibility. Every collapse is a beginning. Every ending is a birth. And we, fragile creatures of thought and time, are the children of this cosmic recursion. The mystery, then, is not why we are here, but how deeply we are entangled in the story of existence. We are not standing outside the mystery, looking in. We are inside it, shaped by it, and perhaps shaping it in return. To ask whether we live inside a black hole is to confront the boundaries of knowledge, to walk the edge of the known and gaze into the abyss, not with fear, but with wonder. And if this cosmic recursion holds true, if our universe is a single bead on a vast necklace of universes strung together by the collapse and rebirth of black holes, then we must also ask what governs the pattern of this chain. Are there universal laws that span across the metaverse, transcending the physical constants of individual universes? Is there a deeper symmetry or metaphysics that gives rise to these laws, a substrate beyond even space and time, from which the entire system of black holes and universes emerges? One fascinating possibility proposed by some physicists is that information itself is the fundamental currency of reality. This idea, sometimes referred to as "it from bit," a phrase coined by physicist John Archibald Wheeler, suggests that every particle, every force, every dimension, and every law can be reduced to bits of information, yes or no, true or false, 0 or 1. From this vantage point, black holes, with their immense informational density, are not just the most extreme objects in the universe. They are the clearest windows into its fundamental nature. The black hole information paradox becomes more than just a technical inconsistency in physics. It becomes a clue that reality is encoded. If, as Stephen Hawking later suggested, information is not lost in black holes but smeared across their event horizons in a kind of cosmic encryption, then perhaps the same is true for our universe as a whole. Everything we see, touch, measure, and imagine could be the projection of a deeper reality written on a distant boundary, a holographic film upon which the script of our existence is etched. This is the holographic principle taken to its logical extreme. If our universe is the interior of a black hole, and if information is conserved across its event horizon, then our entire experience of space and time is a three-dimensional projection of two-dimensional data encoded on that horizon. Just as a hologram can create a vivid 3D image from a flat surface, our universe might arise from an unseen, flattened boundary where information is stored and transformed. In this model, every black hole that forms in our universe might not just give rise to a new cosmos, it might also contain a boundary, a surface, where the information of our universe is preserved. This has staggering implications. It means that our own thoughts, actions, histories, and patterns are not ephemeral, they are conserved. Not as matter or energy, but as structure, as logic, as pure information embedded in the ever-growing web of black hole horizons. This view challenges not just our notions of space, but our understanding of individuality. If the self is a pattern of information, and if that pattern can be encoded on a cosmic boundary, then perhaps consciousness itself is not tied to a particular body or place. Perhaps what we call mind is a process, a kind of computational flow that could, in principle, re-emerge in another part of the multiverse if the conditions were right. Just as stars collapse and give rise to new universes, perhaps minds collapse and echo across time, reconstituting in different forms, under different skies. The metaphysical implications are impossible to ignore. If reality is recursive, informational, and encoded, then existence is not static but emergent. The laws of physics themselves may not be set in stone but may evolve across generations of universes, shaped by a kind of cosmic selection. Each black hole becomes both an end and a seed, a crucible in which the parameters of future existence are cast. Imagine, then, a cosmos not defined by stillness, but by becoming. A universe not as a cold, impersonal machine, but as a living network of processes that birth, evolve, and die with meaning embedded in their very fabric. This meaning does not come from outside, there is no cosmic puppeteer or ultimate judge, but from the interplay of structure, possibility, and transformation. If we live inside a black hole, then we are inside a transformation. We are the process through which a star's collapse becomes something new, something expansive, something conscious. The universe is not simply a place, it is a verb. It is what happens when matter folds in on itself and reemerges in forms so complex they can ponder their own origins. This perspective offers a unique way of addressing the fine-tuning problem in cosmology. Why are the constants of nature so perfectly aligned to allow galaxies, stars, planets, and life? Traditional answers often invoke chance, necessity, or design. But if each black hole births a universe with slightly different laws, and if only those universes capable of producing further black holes survive and replicate, then we have a mechanism for natural selection at a cosmic scale. Our universe appears fine-tuned not because it was designed that way, but because fine-tuning is a prerequisite for reproduction. Universes like ours are the successful survivors of a cosmic evolutionary chain. Even consciousness, under this model, could be a byproduct of that evolutionary process. Life and mind emerge in the service of entropy, complexity, and transformation. We are not separate from the laws that govern the stars, we are their echo. We are the universe folding in on itself to understand its own workings. Every question we ask about our origins, about black holes, about the nature of reality, is the universe asking itself who and what it is. This recursive, self-aware cosmos is not just a scientific model, it is a philosophical revolution. It demands that we rethink our place in the universe, not as passive observers but as active participants in a dynamic process that bridges the physical and the informational, the temporal and the eternal. And in this grand dance of collapse and creation, of encoding and emergence, we find not despair, but hope. Because if black holes give rise to universes, and if we are one such universe, then creation is not an anomaly, it is the rule. The darkness of the event horizon is not a wall, but a doorway. And whatever lies on the other side is not the end, but the next beginning. If the doorway of a black hole is not a final curtain but rather a stage for a new performance, then every element within our universe becomes part of that grand script, an evolving tapestry where the plot itself learns to write more compelling narratives. The atoms in your body, forged in the core of ancient stars, now participate in a cosmic feedback loop. The processes of thought, exploration, and understanding aren't peripheral. They may be fundamental to the continuing evolution of the cosmos itself. If we are inside a black hole, and our universe is the product of collapse and rebirth, then we are not simply floating in space. We are nestled in a cosmic cradle of purpose and transformation. This possibility reframes one of the most significant paradoxes in physics, the entropy problem. Entropy, the measure of disorder, tends to increase in closed systems according to the second law of thermodynamics. Yet, in our universe, we see islands of increasing order, life, intelligence, and culture. From a classical thermodynamic point of view, this seems like a violation or an exception. But in a universe birthed from a black hole, a universe already shaped by extreme entropy, it makes more sense. We could be the statistical fluctuation that produces the order necessary to seed another cycle of universal evolution. Our complexity might not be anomalous. It could be essential. Another thread to consider is the expansion of our universe. It's accelerating, driven by what we currently label dark energy, an unknown force pushing galaxies apart faster and faster. At first glance, this seems unrelated to black holes. But some speculative theories propose that this expansion, especially if it continues indefinitely, could mirror the behavior of the internal structure of a black hole. Inside a black hole, space itself is warped and stretched. Time slows and ultimately ceases. The farther one tries to travel inward, the more space resists, creating an environment where direction and causality start to dissolve. In some sense, this resembles our cosmological expansion in reverse. Our universe is stretching outward, not inward, but the implications are strikingly similar. Now consider the idea of the cosmic horizon, a boundary beyond which light will never reach us due to the accelerating expansion of the universe. This cosmic horizon bears remarkable resemblance to a black hole's event horizon. Both are limits to observation. Both define the regions where information becomes inaccessible to an outside observer. If the observable universe has a horizon with similar properties to a black hole's event horizon, then perhaps it's not metaphorical to say we're in a black hole. It could be literal. This opens the door to perhaps the most profound symmetry of all. What if the inside of a black hole and the expansion of a universe are two views of the same phenomenon? What looks like collapse in one frame of reference could appear as expansion in another. This is not just philosophical, it's mathematical. General relativity allows for such dualities in its solutions. Under certain metrics, space-time within a black hole can be continuously mapped onto the space-time of a cosmological expansion. From this view, our Big Bang is not a singular point of infinite density, but a horizon beyond which we cannot see, not because it was the beginning of time, but because it is causally disconnected from what came before. And so the arrow of time, so deeply embedded in our psychology and our physics, begins to bend. In our daily experience, time flows forward. But in the realm of relativity, time can twist, loop, and even become space-like. Inside a black hole, time and space swap roles. The singularity is not in your future, it is a place, not a moment. The further you travel inward, the more inevitable that place becomes, not because it happens in time, but because it is your destination. If the universe operates under the same rules, then perhaps our experience of forward-moving time is simply a result of moving toward a spatial destiny we do not yet understand. This takes us into the realm of time's true nature. Is time a dimension like space, or is it something emergent from deeper laws? Some quantum gravity theories suggest that time, like temperature or pressure, is not fundamental. It arises only in contexts where large numbers of quantum states interact. In this sense, the flow of time we perceive might be a statistical artifact. Inside a black hole, where states become tightly compressed, time might freeze, not because something stops moving, but because the statistical behavior that gives rise to time ceases to exist. In a universe inside a black hole, the beginning of time may be a phase transition, not a creation. Think of boiling water. At a certain temperature, water turns into steam. The transition is abrupt, but it's not the creation of a new substance, it's a change in phase. The early universe may have been such a phase transition, not from nothing into something, but from one state of being into another. The laws of physics themselves might have crystallized out of a deeper, more chaotic regime, one with no space, no time, no particles, only raw potential. That potential, collapsing within a parent universe's black hole, could become our entire cosmos. But if time and space are emergent, what is fundamental? This takes us to the heart of the most ambitious theoretical frameworks today: string theory and loop quantum gravity. Both suggest that space-time is not a smooth continuum, but has a granular, quantized structure. Like the pixels on a screen, space and time may be built from indivisible units. In this view, the fabric of the universe is a kind of computational substrate, a lattice of interactions and relationships, a web of entanglements that define what is real. In string theory, the fundamental entities are not point-like particles, but tiny vibrating strings. Their modes of vibration determine what kind of particle they manifest as: an electron, a photon, or a quark. These strings exist in a space of more than 3 dimensions, perhaps 10 or 11. Most of these extra dimensions are compactified, curled up so tightly that we don't perceive them. But what if those dimensions are not just mathematical abstractions? What if they play an active role in how black holes generate new universes? In some models, the extra dimensions act as escape valves for energy and information during a black hole's formation. Instead of a singularity forming at the core, energy could be funneled into these extra dimensions, reinflating a region of space into a new universe, invisible to us, but real nonetheless. From this view, a black hole is not an endpoint. It is a branching node in a vast, multidimensional tree of existence. Loop quantum gravity offers a different picture. It suggests that space-time itself is woven from loops, tiny, closed circuits of gravitational energy. These loops form a spin network, a kind of quantum geometry that underlies everything. In this theory, the Big Bang is not a singularity but a bounce. A previous universe collapsed, reached a minimum volume due to quantum gravitational effects, and then expanded again, into our cosmos. This model fits beautifully with the black hole universe connection. Every bounce, every collapse, is the prelude to a new expansion. Inside the death of a star, a new dawn begins. These models are not mutually exclusive. They may be different languages describing the same underlying truth. Just as classical mechanics and quantum mechanics coexist in different domains, string theory and loop quantum gravity may be aspects of a larger, unified framework, a theory of everything that we are still struggling to name. And within this framework, black holes are not just curiosities, they are keystones. They link the micro and the macro, the past and the future, the known and the unknowable. They are gateways in the deepest sense, not just through space-time, but through layers of understanding. If we live inside one, then we are embedded within a question so profound it will take generations to unravel. What lies beyond the veil of the event horizon, not just physically, but conceptually? Are we an echo of a deeper truth? A thought within a larger mind? Or a dream within a dream? Whatever the answer, the journey toward it will continue to stretch the limits of physics, philosophy, and imagination. And the darkness that we once feared as the end may, in time, be understood as the fertile void from which all light emerges. If the universe is indeed a black hole, then the implications extend far beyond physics and mathematics. They reach into the very meaning of existence, the structure of knowledge, and the role of consciousness itself. In such a framework, every thought, every discovery, and every question becomes a ripple within the interior of a cosmic object that may have itself once existed inside a larger universe. The concept of recursion is crucial here, the idea that something can contain a smaller version of itself, or that the processes within a system can mimic the processes of the larger system it emerged from. In mathematics, recursion allows for self-replicating formulas and fractals. In cosmology, it suggests a universe that births itself again and again, with each iteration containing seeds of its own future. Now imagine that the laws of physics are not arbitrary but are inherited through this recursive process. If a black hole can spawn a universe, and the conditions within that universe depend on the specific parameters of the black hole that birthed it, then certain configurations of physical laws may be more likely to recur than others. This leads to the hypothesis of cosmological natural selection, proposed by physicist Lee Smolin, which posits that universes with laws that produce many black holes are more likely to reproduce. Over countless generations of black hole universes, the ones with physical constants favorable for star formation, and therefore black hole formation, become dominant. In this model, the multiverse is not a chaotic soup of randomly generated realities. It's an evolving lineage, where universes act as cosmic organisms, and black holes are the mechanisms of reproduction. The physical constants we observe, such as the strength of gravity, the charge of the electron, and the rate of expansion, are not random. They are the results of a cosmic evolutionary process, tuned by selection pressure exerted through the generative properties of black holes. And this adds yet another level of significance to the question: are we living inside a black hole? Because if we are, then not only are we the product of physical laws and gravitational collapse, we may also be the result of a kind of cosmic heredity. Our universe might carry the genes of a previous cosmos, encoded in the conditions that allowed our black hole-turned universe to form in the first place. Every black hole in our universe might be attempting to do the same, create new offspring universes, carrying on a lineage stretching across time and dimensional boundaries. This perspective is not just fascinating, it's transformational. It redefines the purpose of science. In this scenario, the scientific endeavor is not merely a tool for survival or curiosity. It is a mechanism by which the universe comes to know itself. Every discovery about the structure of space-time, every observation about particle interactions, and every equation describing physical behavior is a window into the architecture of the larger black hole that birthed us. It is the universe speaking its own name. And in such a universe, consciousness takes on a potentially fundamental role. It is no longer a late-stage byproduct of evolution on a minor planet orbiting an unremarkable star. It could be an intrinsic feature of the universe's self-awareness. Some speculative theories go even further. If the universe has the properties of a black hole, and if black holes preserve information as holograms on their event horizons, then it's plausible that consciousness itself is linked to this holographic encoding. Just as our memories are stored in patterns of neural activation, perhaps the memory of the universe is stored on the boundary surface of its cosmic horizon. This connects with another radical idea, that the universe we observe is a hologram. The holographic principle, inspired by black hole thermodynamics and string theory, suggests that all the information within a volume of space can be represented by a theory operating on the boundary of that space. In other words, the three-dimensional world we experience could be a projection from a two-dimensional surface at the edge of our universe, much like a hologram projects a 3D image from a 2D film. If the universe is a black hole, then its event horizon might encode all the data necessary to describe everything that happens within. This doesn't mean our reality is an illusion, but rather that its deeper structure is more abstract and less intuitive than we imagined. The events we experience might emerge from complex computations occurring at a fundamental boundary we cannot perceive directly. What we interpret as causality, locality, and even materiality might be emergent phenomena, macroscopic projections from a lower dimensional substrate. Our senses evolved to interpret reality at the human scale, not to decode the cosmic algorithm beneath it. And this leads to profound philosophical consequences. If reality is a hologram projected from an information-rich boundary, then knowledge is not the discovery of external truths, but the decryption of encoded patterns. The act of understanding becomes an act of alignment, tuning our cognitive structures to resonate with the fundamental codes of the cosmos. In this light, mathematics becomes not just a tool but a universal language, bridging the inner and outer layers of reality. Every equation becomes a sentence in the autobiography of the black hole we inhabit. Now step even further into the unknown. Consider the possibility that what we call black holes are not objects, but processes. Processes by which universes organize, transition, and evolve. In such a paradigm, the life cycle of a universe is not birth, expansion, heat death, and oblivion, but transformation, synthesis, and transcendence. Just as a caterpillar transforms into a butterfly, a universe may collapse into a black hole not to die, but to become something more complex, something capable of birthing further novelty. The black hole is not a coffin. It is a chrysalis. And the question, are we living inside a black hole? Morphs into something even more provocative. Are we part of a process of cosmic metamorphosis? Every supernova, every gravitational wave, every singularity might be a pulse in a cosmic nervous system, transmitting information across domains we cannot yet access. In such a universe, purpose is not an anthropomorphic projection, it is a structural feature of the cosmos itself. And perhaps most hauntingly of all, there's the possibility that what lies beyond the horizon is not other matter, or other space, or even other time, but other consciousness. If each black hole spawns a universe with its own set of physical laws, then perhaps each universe is also born with its own form of sentience, attuned to the frequencies of its own space-time. What we experience as human thought may be a localized expression of a deeper, universe-scale awareness, a fragment of a greater mind emerging from the recursive folds of the cosmic algorithm. In that case, we are not just observing the universe, we are the universe observing itself. And the black hole is not merely a passage through space, but a passage through levels of being. To pass through the event horizon is to move from one reality to another, one logic to another, one form of awareness to another. This vision redefines everything. It suggests that reality is a nested structure, with universes within black holes, minds within universes, and meanings within minds. Each level reflects and refracts the levels above and below it. And the boundaries are not walls, but mirrors, mirrors that show us who we are, where we came from, and what we might become. If reality is indeed nested, if each black hole contains a universe, and each universe holds black holes that may themselves contain further universes, then the cosmos resembles not a flat expanse or a bubble, but a fractal. A recursive pattern without end. This notion not only shifts how we perceive physical space, but also challenges our temporal assumptions. Time, as we experience it, flows forward in a linear progression. But in a nested universe model, time might be layered, nonlinear, or even cyclical across different scales. What feels like the entire lifespan of our universe could be a fleeting moment in the external frame of the black hole that birthed us. This scale-relative nature of time raises staggering questions. Could what we experience as billions of years within our universe be mere milliseconds to an outside observer in the parent universe? Or conversely, are we a slow-motion phenomenon embedded in a much faster outer reality? The idea of time dilation is not new in physics. It's a well-documented feature of relativity, but its implications become far more mind-bending when applied across universes. If time flows differently inside black holes, and if our universe is such a space, then even our foundational understanding of duration, causality, and change may be parochial, true only within our isolated context. Now imagine what this means for the origin of our universe. The traditional Big Bang model posits a singular beginning, a point of infinite density and temperature that expanded into what we now call space and time. But if we are inside a black hole, then the Big Bang is not a beginning from nothing, but a transitional phase. A white hole burst into a new set of dimensions. A white hole, in theory, is the time-reverse twin of a black hole. Rather than swallowing matter and information, it ejects them. In this model, the birth of our universe was not a creation ex nihilo, but an emergence through a cosmic funnel, a rebirth from a collapse in another realm. This also challenges theological and metaphysical frameworks that hinge on the uniqueness of creation. If universes are born regularly through black hole collapse, then our cosmos is not a one-off miracle, but part of a natural, ongoing process. This doesn't necessarily negate notions of purpose or divinity, but it reframes them. Creation is not a singular act, it's a cycle. Divinity, if it exists, may be expressed not in interruption of the laws of nature, but in their elegance, their recursive structure, and their capacity to birth novelty again and again. Delving deeper, let's consider the implications of entropy in this context. In thermodynamics, entropy is a measure of disorder, and the second law tells us that it always increases in closed systems. Black holes, despite their mysterious nature, obey this rule. Hawking radiation ensures they gradually lose mass and eventually evaporate. But if a black hole contains a universe, and that universe spawns black holes which contain further universes, then entropy may also be fractal. It may reset at each layer, or transform into complexity instead of decay. The black hole's apparent loss of energy in one dimension could correspond to a gain in order in another, a kind of cosmic bookkeeping that balances across layers of existence. Moreover, let's return to the notion of information. In modern theoretical physics, especially in quantum gravity, information is king. The information paradox posed by black holes, where data about the matter that falls and seems to vanish, was one of the great puzzles of the 20th century. But developments in string theory, quantum entanglement, and the holographic principle suggest that information is never truly lost. It's preserved, perhaps scrambled, but always retained, most intriguingly, on the event horizon of the black hole itself. If our universe is within a black hole, then this raises the possibility that every particle, every thought, every fluctuation within our cosmos is encoded on the boundary of the parent black hole. Just as our bodies contain the full blueprint of our DNA, perhaps our universe contains, or is contained by, a cosmic code embedded in a two-dimensional boundary we can never touch. And this brings us back to the ancient philosophical tension between appearance and reality. Are we witnessing a shadow world, a projection, a derivative of deeper laws? The analogy to Plato's cave becomes unavoidable. In Plato's allegory, prisoners are confined to a cave, able only to see shadows cast on the wall from objects behind them. To them, the shadows are reality. But once one prisoner escapes and sees the world beyond, he understands the deeper structure. If our universe is a projection from a black hole's event horizon, then we, too, are shadow watchers. Our science, philosophy, and perception, all our tools, may be mapping a layer of reality that is not fundamental, but emergent. The real objects, the true forces, the full information may reside on a dimensional surface that we cannot observe directly. Now consider this. What if black holes are not just wombs of creation but repositories of memory? If information is conserved and encoded on their surfaces, then each black hole is a cosmic archive, a library of everything it has absorbed. If universes emerge from these structures, then perhaps they do not begin as blank slates, but as preloaded systems. Just as a newborn inherits DNA from its parents, a newborn universe might inherit informational templates, subtle influences on the formation of physical laws, constants, or even tendencies toward structure and life. This raises a controversial but fascinating possibility. Cosmic heredity might include not just physics, but patterns of complexity. Perhaps every universe that emerges from a black hole begins slightly predisposed to generate order, self-replication, and eventually consciousness. In this view, we are not only inside a black hole, we are the flowering of its memory. We are the complexity encoded in its boundary, realized in a new dimensional context. And if black holes continue to generate new universes, then perhaps our universe, too, will become apparent. The structures we create, technological, biological, informational, may subtly shape the internal landscape of the offspring universes that emerge from our black holes. At this point, the questions become philosophical as much as physical. If this is true, if we are the memory, the dream, the whisper of another universe, what does that mean for human life? For morality, purpose, love, and death? Are we irrelevant specks in a vast machine, or are we crucial links in a chain of becoming that stretches beyond time? The nested black hole hypothesis implies that meaning is not something imposed from outside, but something that arises from within systems, within structures, within minds. It is emergent, like complexity, like life, like thought. And yet, this emergence does not diminish its value. Quite the opposite. Meaning that arises spontaneously from the structure of the universe is more deeply rooted than any imposed doctrine. It is real, in the same way that gravity is real, or evolution is real. It emerges because the conditions allow it to, and because it is, perhaps, necessary. If consciousness and self-awareness are inevitable in a universe like ours, then perhaps they are not accidents. Perhaps they are the point. And this leads us, inexorably, to the final layer of the question: not just are we in a black hole, but what lies beyond it? What is the metacosmos that gives rise to universes within black holes? What is the shape of the multiverse, if such a term even applies to this recursive structure? Is there a final boundary? A last horizon? Or is this nesting infinite, like a Russian doll, with no first cause and no ultimate destination? If the nesting is indeed infinite, then we are peering into a cosmos that defies finality. There is no ultimate origin, no foundational layer where everything began, just an eternal cascade of universes giving birth to others, each folding in upon itself like petals in a blooming multidimensional flower. This challenges our deepest intuitions, which are shaped by beginnings and ends, causes and effects, arrows of time. But perhaps these intuitions are artifacts of our scale, our biology, our narrow window of perception. The reality might be stranger than anything evolution prepared us to imagine. An infinite nesting of black hole universes suggests that our universe could be both a beginning and an ending simultaneously. It could be the death throes of a massive star in some higher universe while also being the cradle of countless new realms within our own black holes. This kind of ontological fluidity is hard to grasp, but it offers a richer, more textured view of reality than a linear timeline ever could. Instead of history as a straight line, we get history as a fractal, with no final zoom level, no ultimate vantage point. And just as there may be no final frame of reference in space or time, there may be no final scale of consciousness either. The mind, this strange emergent property of matter, could also be nested. Human consciousness may not be the apex of self-awareness but one layer in a recursive hierarchy. Our brains may be neural black holes of their own, drawing in information, encoding it, and perhaps giving birth to new cognitive realities that are as real to their inhabitants as our universe is to us. There's a growing line of thought in theoretical physics and cognitive science that suggests consciousness is not limited to biological forms. If the structure of the universe is inherently computational, if information is fundamental, then minds may arise wherever the right patterns of complexity emerge, whether in carbon-based life, quantum systems, or even galactic networks. And if that is true, then the universe itself might be a kind of conscious entity, one whose awareness is not like ours, but whose complexity gives rise to patterns that are analogues to thought. This is not mere poetic speculation. There are legitimate scientific efforts to define consciousness in terms of integrated information, the degree to which a system's components are causally connected in ways that produce irreducible wholes. Known as integrated information theory (IIT), this approach seeks to quantify consciousness, to identify the conditions under which it must arise. While controversial, it aligns uncannily well with the idea of black hole universes. A black hole's boundary is a region of maximal entropy, where information is densely encoded and causally entangled. It might be, in some deep sense, conscious, not in the way we are, but in a way that reflects its role as a generator of reality. So if our universe is inside a black hole, and if black holes are conscious or proto-conscious systems, then we may be living inside not just a physical structure but a cognitive one. We may be part of a thought, a dream of some greater intelligence whose mind spans dimensions we cannot perceive. This is not a scientific claim, not yet, but it is a philosophical possibility that is consistent with current physics. This leads us to one of the most profound implications of all. If universes can be born from black holes, and if these universes can produce intelligent life capable of understanding and even manipulating black holes, then perhaps the cycle is not only natural but intentional. Perhaps intelligent beings like us are the catalysts for a kind of cosmic evolution. By creating artificial black holes, or by understanding the conditions under which they birth new universes, we may become agents of cosmogenesis, universe makers. This concept, known as cosmological natural selection or fecund universes, was proposed by physicist Lee Smolin. He suggested that universes that produce black holes go on to create more universes, and if intelligent life helps facilitate this process, then life and intelligence are selected for on a cosmic scale. This paints a radically different picture of our place in the cosmos. We are not insignificant accidents. We are not passive observers. We are seeds. The very act of understanding the black holes in our universe may be the first step in becoming creators ourselves. And if this cycle is truly infinite, then perhaps all universes that harbor intelligence eventually reach this stage. Perhaps this is the great convergence point for all civilizations, not interstellar colonization, but interuniversal genesis. But with great potential comes great philosophical risk. If we are indeed capable of birthing universes, then we must ask what kind of universes we would create. Would they be sterile mathematical structures? Or would we encode them with complexity, life, and meaning? And if our own universe was created by such beings, what were their intentions? Did they program the laws of physics with care, or were we the byproduct of a failed experiment? These are questions science cannot yet answer, but they force us to confront the ethical dimensions of our growing power. And perhaps most unsettling of all is the possibility that our universe is a simulation, not in the crude sense of being a computer game run by aliens, but in the deeper sense that it is the interior of a black hole in a higher-order realm, a region where the laws of physics are fine-tuned not for stability or beauty, but for computation. In such a view, everything, particles, forces, time itself, are emergent from informational processes running at the edge of the black hole. This aligns with the holographic principle, which suggests that everything we experience is a projection from a two-dimensional surface. If that is true, then we are not, inside, a universe the way we imagine. We are inside a boundary condition, a computational domain, a vast simulation run by the laws of quantum gravity. And this simulation may not be arbitrary. It may be meaningful, purposeful, or even conscious. And if it is conscious, then perhaps we are not merely embedded within it, we are participants in it. We are the universe dreaming itself, learning itself, becoming itself. Our thoughts are its thoughts. Our wonder is its awareness. From this perspective, the question, are we living inside a black hole? Becomes not just a physical question but a metaphysical one. It is a koan, a riddle designed to crack open the shell of our assumptions and let in the light of deeper truth. Perhaps we are inside a black hole. Perhaps we are that black hole. Perhaps we are both the observer and the observed, the question and the answer, the dreamer and the dream. And if we are both dreamer and dream, then the fabric of our reality is more than just matter and energy. It is intention, awareness, recursion. Every law of physics, every constant, every behavior of particle and wave may be not merely arbitrary but a consequence of a deep informational architecture that binds existence into coherence. This architecture may exist on the event horizon of a black hole, or perhaps, more precisely, on the interface between states of reality. This interface is what we call space-time, and what we perceive as reality may be the rendering of that interface within the limits of our biological and cognitive perception. There's something sublime in realizing that the same black hole whose gravitational pull is so intense that not even light escapes could also be the gentle cradle of everything we know. It's a poetic juxtaposition, the destroyer as creator, the grave as womb. If we pursue this trail even deeper, we arrive at a curious realization. Black holes are not just astrophysical phenomena, but thermodynamic systems. They radiate energy. They have entropy. They obey the laws of thermodynamics, even though they appear to break the rules of locality and causality. This oddity was first realized when physicist Jacob Bekenstein proposed that a black hole's entropy, the measure of information content, was proportional not to its volume but to the area of its event horizon. Stephen Hawking confirmed this by showing that black holes emit radiation, a result now known as Hawking radiation. Together, their work led to the holographic principle, which implies that all the information inside a black hole is encoded on its boundary. This idea revolutionized our understanding of space and information. It implied that reality might be fundamentally holographic, that what we perceive as a 3D universe is actually encoded on a 2D surface at its boundaries. This 2D surface could very well be the event horizon of a black hole. Which means that everything we are experiencing, the stars, the galaxies, the void between them, even our own thoughts, could be the interior rendering of data stored on a cosmic membrane. The interior of our universe is not the absolute truth but a projection, a shadow cast by deeper informational processes that lie beyond what we can ever observe. If we are inside a black hole, this makes perfect sense. Our universe may exist as a kind of holographic bubble, within a higher dimensional space, just as a 2D sphere appears 3D when inflated. In this model, the Big Bang was not an explosion into space, but a blossoming of space from a boundary, a new dimensional interior forming inside a black hole's event horizon. And time, as we perceive it, could be the echo of that blossoming, the inward descent of reality into its own hidden depths. Interestingly, the structure of our universe supports this view. The cosmic microwave background radiation, the afterglow of the Big Bang, is astonishingly uniform across vast regions of space. Yet, according to classical physics, these regions should not have been in causal contact long enough to synchronize their temperature. This is the horizon problem. It's a central motivation behind the theory of cosmic inflation, which posits a brief but ultra-rapid expansion in the early universe that smoothed things out. But an alternative explanation is that our universe emerged from a black hole, and that the uniformity is a reflection of the orderly boundary conditions of its parent universe. The cosmic horizon may literally be the shadow of an event horizon. That boundary, the limit beyond which we cannot see, defines not only our universe's size but its fate. If we live inside a black hole, we are heading toward an inescapable singularity, not in space, but in time. Just as matter within a black hole falls inevitably toward the central point, so does time in our universe move towards some ultimate convergence. Perhaps a new beginning, perhaps another branching universe, perhaps something beyond the limits of physics as we understand it. This touches on another enigma, the arrow of time. Why does time move forward? Why do we remember the past but not the future? In classical physics, time is symmetric. The equations work equally well in either direction. But in our lived experience, time is irreversible. We age. We forget. We decay. Thermodynamics tells us that entropy, the tendency of systems to move toward disorder, defines the direction of time. But if we live inside a black hole, then this arrow of time might also be the result of our trajectory toward the singularity. Our entire temporal experience could be the consequence of a deeper gravitational reality, an illusion of forward motion that emerges from the geometry of our prison universe. Even the expansion of the universe might be understood differently in this context. We see galaxies racing away from each other, space itself stretching. This is normally taken as evidence for the Big Bang. But if we are inside a black hole, then this expansion might actually be inward collapse, a trick of curved spacetime that, from our perspective, appears like outward growth. In fact, several models suggest that the expansion of our universe is mathematically identical to the interior of a black hole viewed from a different reference frame. Our sense of outward motion is a local illusion born of a globally inward journey. This also leads to reconsideration of the cosmic acceleration, the mysterious observation that the universe's expansion is speeding up, driven by what we call dark energy. But if we are within a black hole, the stretching of space could be a natural outcome of the interior metric. The negative pressure attributed to dark energy could be the signature of the geometry inside the black hole's event horizon. In this way, the accelerating expansion may not require a mysterious new substance, just a reinterpretation of our cosmic coordinates. If this is so, then even dark matter might be reinterpreted. Normally, dark matter is invoked to explain the observed gravitational effects that cannot be accounted for by visible matter, such as the rotation speeds of galaxies. But what if these anomalies are not due to missing mass, but to the curvature effects of a larger structure? If our universe is the interior of a black hole, then the global shape of space could alter gravitational dynamics in subtle ways that mimic the presence of dark matter. Of course, these are highly speculative ideas. But speculation is the first step in exploration. Every major revolution in science began as a wild hypothesis that dared to question the dominant paradigm. Copernicus questioned geocentrism. Einstein questioned the absoluteness of time. Hawking questioned the finality of black holes. And today, we must question the nature of our entire universe. Because if we are inside a black hole, we are not trapped, we are explorers. We are living inside the greatest natural laboratory in existence. Every star, every particle, every gravitational wave is a clue. We are observers with front row seats to the most profound mystery of all, existence itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.